Hello and welcome. I'm glad you're here. Tonight we're going to talk about something you've seen every day of your life. Something so familiar that it's easy to forget how extraordinary it actually is. We're going to talk about the sun, that bright disk in the sky that warms your face, that makes shadows stretch across the ground, that turns the clouds pink and gold at the end of the day. But we're going to look at it differently tonight. We're going to see it not just as a source of light, but as a mystery, a furnace, a timekeeper, and in a very real sense, the reason you exist at all. Before we begin, I want to ask you something. How was your day? Really, I mean it. Whether it was long or short, easy or difficult, full of small victories or quiet frustrations, I'd love to hear about it. Leave a comment below and tell me. And if you're finding some peace here, some comfort in these quiet explorations of the cosmos, consider subscribing to the channel. It helps more than you might think, and it means we can keep taking these gentle journeys together. All right then, get comfortable. Let the weight of the day settle into your pillow. Let your breathing slow. Now, let's begin. The sun is 4.6 billion years old, roughly the same age as Earth itself. Think about that number for a moment. 4.6 billion. It's so large it almost loses meaning, doesn't it? But here's what makes it beautiful. Both the sun and the earth were born from the same cloud, the same swirling mass of gas and dust that collapsed under its own weight, spinning faster and faster, heating up in the center until it ignited into our star. And from the leftover debris, from the material that didn't fall into that central fire, the planets formed, including the one you're lying on right now. In a very real sense, the sun and earth are siblings. They share the same birthday, the same cosmic nursery, the same origin story. Every atom in your body, every breath you take, every beam of sunlight that's ever warmed your skin, it all traces back to that moment, 4.6 billion years ago, when a cloud decided to become a solar system. Maybe that makes you feel small, or maybe it makes you feel connected to something vast and ancient. Perhaps it's both. Either way, you and the sun have been travelling through space together for longer than mountains have existed, longer than oceans have rolled, longer than anything alive has been alive. And you're both still here, we spinning through the darkness, bound together by gravity and history. Every second the sun converts 600 million tons of hydrogen into helium. 600 million tons every single second. It's doing it right now as you read these words, as you breathe in and out, as you settle deeper into wherever you are. This is the same process that powers hydrogen bombs, the most destructive weapons ever created, but happening continuously in a controlled cascade of fusion at the heart of our star. Imagine that, a cosmic furnace so powerful it's essentially a perpetual thermonuclear explosion, held together only by its own immense gravity. And yet, from here, 93 million miles away, it's just gentle. It's the warm patch of sunlight on the floor where a cat likes to sleep. It's the glow through your curtains in the morning. The sun is both a roaring inferno and a quiet companion, depending on your distance and your perspective. And this has been happening for billions of years, long before there were eyes to see the sunlight. Long before there was life to evolve beneath its rays, the sun was there, fusing hydrogen, releasing energy, shining into the void. It will keep doing this for billions more years. In that sense, the sun is perhaps the most reliable thing in the universe, at least in our small corner of it. The light reaching your eyes right now left the sun's surface about 8 minutes and 20 seconds ago. This means you're always seeing the sun as it was in the very recent past, never as it is in this exact moment. Right now, as you think about this, the current sun, the sun as it exists in this precise instant, is invisible to you. You won't see that version for another 8 minutes and 20 seconds. It's a strange thought, isn't it? We think of sight as instantaneous, as something that happens now. But light, for all its speed, still takes time to travel. And in that time, the universe changes. The sun you see is slightly younger than the sun that exists. You're looking into the past every time you glance at the sky. And here's something even stranger. If the sun were to suddenly vanish, just blink out of existence, we wouldn't know for over 8 minutes. The light would still be travelling toward us, carrying the image of a sun that no longer existed. For 8 minutes and 20 seconds, we would continue living in a solar system with a star, even though the star was gone. The Earth would continue its orbit, held by gravity that also takes time to propagate, and then, all at once, everything would change. Darkness, cold, chaos. But for those 8 minutes, we'd have no idea. We'd just be living our lives, seeing sunlight, completely unaware. Of course, the sun isn't going anywhere, but the delay remains, a reminder that even light has limits, and that the universe is far stranger than our everyday experience suggests. The sun contains 99.86% of all the mass in our entire solar system. Everything else, all the planets, all the moons, all the asteroids and comets and dust and gas floating between the worlds, makes up barely 0.1%. Jupiter, the largest planet, is just a rounding error compared to the sun. Earth is barely worth mentioning. This puts things in perspective, doesn't it? We think of the solar system as this collection of worlds, this family of planets orbiting together, and in a sense, that's true. But really the solar system is the sun, and everything else is just debris. We're the leftovers, the scraps, the bits that didn't fall into the center, and yet from these scraps complexity emerged. Life, thought, consciousness, the ability to look up at the sun and wonder about it. There's something humbling about this, but also something empowering. Yes, we're a tiny fraction of the solar system's mass, but we're the fraction that woke up. We're the part that can ask questions, make art, feel love, and try to understand where we came from. The sun is powerful and vast, but it's also just a ball of fusing hydrogen. It doesn't know you exist, but you know it exists. And in that knowledge, perhaps, there's a kind of meaning. A photon of light created in the sun's core takes between 10,000 and 170,000 years to reach the surface. This is one of those facts that seems impossible at first. Light is the fastest thing in the universe, right? It travels at 186,000 miles per second. So how could it take tens of thousands of years to escape the sun? The answer is that the sun's interior is unimaginably dense. A photon born in the core doesn't travel in a straight line. Instead, it bounces. It gets absorbed by an atom, re-emitted in a random direction, absorbed again, emitted again, over and over and over, trillions upon trillions of times. Each step might be tiny, just a fraction of an inch, and each step is in a random direction. So the photon wanders drunkenly through the sun's interior, slowly, very slowly, making its way outward. This is called a random walk, and it's an agonizingly slow process. The photon drifts through the radiative zone, where energy moves only by radiation, not by convection. It zigzags, it backtracks, it moves in every direction except directly up. And over the course of millennia, it eventually reaches the convective zone, Nadasti, where the sun's churning plasma carries it the rest of the way to the surface, and then finally it escapes. It shoots out into space and travels the 93 million miles to Earth in just 8 minutes and 20 seconds. So when you feel the warmth of sunlight on your skin, you're feeling energy that was created thousands, maybe hundreds of thousands of years ago. The photon that's warming your face right now might have started its journey before the pyramids were built, before written language existed, before agriculture, before civilization. It's ancient light, finally free, finally reaching you. The sun's core reaches temperatures of about 27 million degrees Fahrenheit. That's 15 million degrees Celsius if you prefer. Either way, it's a number so extreme it's almost meaningless to us. There's nothing in our everyday experience that comes remotely close to this kind of heat. The surface of the sun is only about 10,000 degrees Fahrenheit, still hot enough to vaporize any known material instantly, but the core is nearly 3,000 times hotter than that. At these temperatures, matter doesn't behave the way it does on Earth. Atoms are stripped of their electrons, leaving bare nuclei bouncing around in a sea of charged particles, a state of matter called plasma. The nuclei are moving so fast with so much energy that when they collide, they can overcome the electromagnetic force that normally keeps them apart. They fuse together, becoming new elements and releasing tremendous amounts of energy in the process. This is the furnace that powers the sun and by extension powers everything on Earth. Every leaf that photosynthesizes, every gust of wind, every wave on the ocean, every breath you take, it all traces back to the fusion reactions happening in the sun's core right now at 27 million degrees. And yet, for all that heat, for all that energy, the sun's core is also a place of remarkable stillness in a way. The fusion happens slowly, atom by atom, over timescales that stretch across billions of years. There's no rush. The sun has time. It's been burning for over 4 billion years, and it will burn for billions more. The core doesn't hurry. It just keeps fusing, keeps releasing energy, keeps shining, one photon at a time. The sun is classified as a yellow dwarf star, as though it's actually white when viewed from space. The name yellow dwarf is a bit misleading. If you were an astronaut floating above Earth's atmosphere, looking directly at the sun, which you shouldn't do of course, but hypothetically, you'd see a white star, not a yellow one. The sun emits light across the entire visible spectrum fairly evenly, which our eyes perceive as white. So why do we call it yellow? Why does it look yellow from Earth? The answer is Earth's atmosphere. When sunlight passes through the air, shorter wavelengths, blue and violet, get scattered in all directions by the molecules in the atmosphere. This is why the sky is blue. The longer wavelengths, reds, oranges, yellows, pass through more easily, so the sun appears yellowish, especially when it's near the horizon and the light is passing through even more atmosphere. The term dwarf is also a bit strange, because the sun is actually quite large compared to most stars, where it's bigger and brighter than about 85% of the stars in the galaxy. But in astronomy, dwarf just means it's a main sequence star, a normal hydrogen-fusing star in the stable middle part of its life. It's not a giant and it's not a supergiant, it's just a regular star. A good, solid, dependable star. And maybe that's the most remarkable thing about the sun. It's not exotic, it's not unusual, it's just an ordinary, middle-aged, medium-sized star in an ordinary part of an ordinary galaxy. And yet, from this ordinariness, something extraordinary emerged. Us. About 1 million Earths could fit inside the sun. It's hard to visualize this, isn't it? Our planet seems so large when you're standing on it, when you're looking at a map, when you're flying across an ocean. But compared to the sun, Earth is almost nothing. 1 million times smaller in volume. If the sun were hollow, you could pour 1 million Earths into it and still have room to spare. And yet, the sun is just a medium-sized star. There are stars in our galaxy, red supergiants like Betelgeuse or UY Scuti, that are hundreds of times larger than the sun. If you placed one of those stars at the center of our solar system, it would swallow Mercury, Venus, Earth, Mars, and possibly even Jupiter. The scale becomes almost absurd. You could fit 1 billion Earths inside some of these giants. 1 billion! It's humbling in a way. We live on this tiny world, orbiting a medium-sized star, in a galaxy full of hundreds of billions of stars, in a universe full of hundreds of billions of galaxies. And yet, this is where we are. This is where life happened. Maybe it's happened elsewhere too. We don't know. But here, on this pale blue dot, circling this ordinary yellow star, something remarkable occurred. Chemistry became biology. Biology became thought. Thought became wonder. And now we can look up at the sun, understand what it is, and feel both small and significant at the same time. The sun loses about 5 million tons of mass every second due to nuclear fusion and solar wind. 5 million tons every second. And yet, despite this enormous loss, it would take trillions of years, far longer than the current age of the universe, to significantly affect the sun's size or behavior. This is because the sun is so massive to begin with. It weighs about 2 times 10 to the 30th power kilograms, or roughly 333,000 times the mass of Earth. Losing 5 million tons per second sounds like a lot, and it is. But compared to the sun's total mass, it's negligible. It's like losing a single grain of sand from a beach every second. You could lose grains for millennia, and the beach would still look the same. Most of this mass loss comes from the fusion process itself, the conversion of hydrogen into helium. When 4 hydrogen nuclei fuse into 1 helium nucleus, a tiny bit of mass is lost. That lost mass becomes energy. According to Einstein's famous equation, E equals mc squared. The rest comes from the solar wind, a constant stream of charged particles flowing outward from the sun in all directions. So yes, the sun is slowly evaporating, slowly dissolving into space, one photon and one particle at a time. But it's doing so at such a gradual pace that, for all practical purposes, it's eternal, at least on human timescales, at least for the next few billion years. The sun will outlast every structure humans have ever built, every mountain, every ocean, and possibly even Earth itself. It's been shining for 4.6 billion years, and it will shine for billions more. And in that continuity, there's something comforting. The sun will be here tomorrow, and the day after, and the day after that, long after we're gone. The sun rotates, but not like a solid object. Different parts spin at different speeds. The equator completes rotation in about 25 days, while the poles take roughly 35 days. This phenomenon is called differential rotation, and it's possible because the sun isn't solid. It's a ball of plasma, ionized gas, where different layers and latitudes can move independently of each other. Imagine if Earth worked this way. Imagine if the equator spun faster than the poles, if different latitudes rotated at different speeds. The continents would shear apart, the oceans would slosh chaotically, the atmosphere would tear itself to pieces. But the sun doesn't have continents or oceans or a solid surface. It's fluid, flexible, constantly churning. And this differential rotation has profound effects. It's one of the key drivers of the sun's magnetic field. As the equator spins faster than the poles, magnetic field lines get twisted and tangled. They wind around the sun like rubber bands, storing energy, creating complex structures. Eventually, these twisted field lines can snap and reconnect, releasing bursts of energy in the form of solar flares and coronal mass ejections. So the sun's rotation isn't just a quirk, it's an essential part of how the sun behaves, how it generates its magnetic field, how it creates the dynamic, ever-changing surface we observe. The sun is never still. It's always moving, always churning, always twisting itself into new configurations. And from here, 93 million miles away, it looks perfectly smooth and calm. The sun's surface temperature is about 10,000 degrees Fahrenheit, but its outer atmosphere reaches millions of degrees. This is one of the great puzzles in solar physics, a mystery that has perplexed scientists for decades. It seems to violate common sense. Normally, as you move away from a heat source, things get cooler. If you step back from a fire, you feel less warmth. If you climb a mountain, the air gets colder as you gain altitude. But the sun doesn't follow this pattern. The visible surface of the sun, the photosphere, is about 10,000 degrees Fahrenheit. That's already hot enough to vaporize any known material, but just above the photosphere, in a thin layer called the chromosphere, the temperature begins to rise, and then, in the corona, the sun's outer atmosphere, visible as a pearly white halo during solar eclipses, the temperature skyrockets to millions of degrees. In some regions, it can exceed 3 million degrees Fahrenheit. How is this possible? How can the atmosphere be hotter than the surface? It's called the coronal heating problem, and we still don't fully understand it. The leading theory involves magnetic fields. The sun's magnetic field lines thread through the corona, and when they twist, tangle, and reconnect, they release enormous amounts of energy. This energy heats the plasma to extreme temperatures, but the details are still being worked out, still being studied by satellites and solar observatories. It's humbling, in a way. The Sun is the closest star to us. We've been studying it for centuries, and yet there are still fundamental questions we can't answer. The universe keeps its secrets, even when they're hiding in plain sight 93 million miles away in the glare of daylight. Ancient cultures worshipped the sun as a deity in nearly every corner of the world. This isn't surprising when you think about it. The sun was the most powerful, most visible, most essential force in their lives. It rose every morning, bringing light and warmth. It made plants grow, made water evaporate and rain fall, made the seasons turn. Without it, there was cold, darkness, death. In Egypt, the sun was Ra, the king of the gods, sailing across the sky in a golden boat. In ancient Greece, it was Helios, driving a chariot pulled by fiery horses. In India, it was Surya, riding across the heavens in a chariot pulled by 7 horses, each representing a colour of the rainbow. The Inca worshipped Inti, the sun god, and built temples oriented to capture the light during solstices. The Aztecs believed the sun needed human blood to rise each day, that without sacrifice it would fail and the world would end. These weren't primitive or ignorant beliefs. They were expressions of a profound truth. We depend on the sun. Our ancestors understood this intuitively, even if they didn't understand the physics. They knew that the sun was life, that it was power, that it was something beyond human control and therefore worthy of reverence. And in a sense, they were right. We still depend on the sun for everything. We just describe it differently now. We talk about photosynthesis instead of divine blessings, about nuclear fusion instead of gods sailing across the sky. But the fundamental relationship hasn't changed. The sun gives and we receive. It shines and we live. Maybe that's worth a little reverence even now. The sun produces enough energy every second to meet humanity's current energy needs for 500,000 years. Think about that. Every single second. Not every hour, not every day, every second. The total amount of energy humanity uses in a year, all the electricity, all the fuel, all the power for every car, every factory, every light bulb, every computer, every device on Earth. The sun produces that much energy in about 1 second. And almost all of it just radiates out into space, unused, unnoticed, a spreading out into the void. Only a tiny fraction, less than 1 billionth, actually hits Earth. And of that tiny fraction, only a small percentage is captured by plants through photosynthesis, or by solar panels, or by the ocean to drive weather patterns. Most of it just bounces off clouds, gets absorbed by rocks, warms the atmosphere, and radiates back out into space. We're living next to an almost inexhaustible energy source. A nuclear reactor that's been running for 4.6 billion years and will run for another 5 billion. It requires no maintenance, no fuel deliveries, no waste disposal. It just shines. And yet, for most of human history, we couldn't harness it directly. We could only use the secondary effects, the warmth, the light, the plants that grew in the sunshine. Now, we're starting to capture that energy more efficiently. Solar panels are becoming cheaper and more effective. We're learning to turn sunlight directly into electricity, to store it, to use it to power our civilization. But even our best efforts only scratch the surface of what's available. The sun's generosity is almost incomprehensible. It gives freely, constantly, without asking for anything in return. Sunspots are areas of the sun's surface that appear darker because they're about 2,700 degrees Fahrenheit cooler than their surroundings. They look dark only by contrast. If you could isolate a sunspot and see it on its own, against the blackness of space, it would still be blindingly bright. It would still glow with intense heat and light. But next to the even hotter surrounding surface, it appears dim, almost black. Sunspots form where strong magnetic fields break through the sun's surface. These magnetic fields are so powerful they suppress the convection currents that normally bring heat from the interior. The result is a region that is slightly cooler, though still hot enough to vaporize any known material instantly. Sunspots often appear in pairs or groups, connected by loops of magnetic field lines arcing through the corona. Ancient Chinese astronomers noticed sunspots more than 2,000 years ago, recording their appearance and disappearance. But it wasn't until Galileo turned his telescope toward the sun in 1610 that European scientists began studying them systematically. Galileo noticed that sunspots moved across the sun's surface, which proved that the sun rotated. This was a radical idea at the time. The heavens were supposed to be perfect and unchanging. Sunspots come and go in roughly 11-year cycles. During solar maximum, the sun can be covered with dozens or even hundreds of sunspots. During solar minimum, there might be none at all for days or weeks. These cycles affect space weather, auroras, and even slightly influence Earth's climate. The sun isn't constant. It breathes, pulses, changes, and sunspots are one of the visible signs of that change, dark freckles on a burning face. The sun has been brightening throughout its life, and is now about 30% more luminous than when it first ignited. This gradual increase in brightness is one of the fascinating slow-motion changes that happen over billions of years. When the sun first formed, when it first began fusing hydrogen in its core 4.6 billion years ago, it was dimmer, cooler, and less intense than it is today. This presents an interesting puzzle. If the sun was 30% dimmer back then, Earth should have been frozen solid. The ocean should have been ice. Life shouldn't have been possible. And yet, we know that liquid water existed on Earth as far back as 4 billion years ago. We have evidence of ancient oceans, of sedimentary rocks that could only form in water. Or this is called the faint young sun paradox. The most likely explanation is that Earth's early atmosphere was very different, probably much thicker, with higher concentrations of greenhouse gases like carbon dioxide and methane. These gases trapped heat, keeping the planet warm despite the dimmer sun. As the sun brightened over billions of years, life and geological processes gradually removed these gases from the atmosphere, cooling Earth back down and maintaining a balance. It's a delicate dance, really. The sun slowly brightens and Earth slowly adjusts, too fast in either direction, and life might not have survived. But the changes happened gradually enough, over hundreds of millions of years, that ecosystems could adapt, that the climate could shift without completely sterilizing the planet. And here we are, still in the habitable zone, still bathed in just the right amount of sunlight. For now, the sun's magnetic field flips polarity approximately every 11 years. North becomes south, south becomes north. The entire magnetic field of our star reverses itself in a cosmic dance that's been happening for as long as the sun has existed and will continue for billions of years to come. This flip doesn't happen all at once. It's a gradual process that takes about a year to complete. During this transition, the sun's magnetic field becomes complex, chaotic, with multiple poles appearing temporarily before settling into the new configuration. And this flip is intimately connected to the sunspot cycle. Solar maximum, when sunspots are most numerous, occurs around the time of the magnetic reversal. Solar minimum, when sunspots are rare, occurs midway between reversals. Why does this happen? It's because of the sun's differential rotation and the way it generates its magnetic field. As the equator spins faster than the poles, magnetic field lines get stretched and twisted. Eventually, the field becomes so tangled that it snaps and reorganizes itself, flipping polarity in the process. Then the cycle begins again. Twist, tangle, flip, over and over. This magnetic cycle affects everything from auroras on Earth to the intensity of solar wind to the frequency of solar flares. When the sun's magnetic field is complex and active, space weather becomes more intense. Satellites can be damaged, power grids can be disrupted, radio communications can be affected. The sun's magnetic heartbeat echoes throughout the solar system, influencing everything within its reach. And it does this on a schedule, regular as clockwork, every 11 years or so. North becomes south, south becomes north. The dance continues. The sun is travelling through space at about 450,000 miles per hour relative to the cosmic microwave background. It takes roughly 225 to 250 million years to complete one orbit around the centre of the Milky Way galaxy. This journey is called a galactic year, or sometimes a cosmic year, and it's hard to wrap your mind around the scale of it. The sun is not stationary. Nothing in the universe is. Right now, as you read this, you're moving. You're spinning with Earth's rotation at about 1,000 miles per hour. You're orbiting the sun at about 67,000 miles per hour, and the sun itself is carrying you around the galaxy at 450,000 miles per hour. You're hurtling through space at speeds that would make any spacecraft look slow, and you don't feel any of it. You just feel still. The last time the sun was in this position in its galactic orbit, dinosaurs had just begun to evolve. Pangaea was still intact. The continents we know today didn't exist yet, and one galactic year before that, the most complex life on Earth was probably just microscopic organisms. The sun has made this journey perhaps 20 times since Earth formed. 20 laps around the galaxy, with Earth in tow, and we're moving in a specific direction toward a point in the constellation Hercules, sometimes called the solar apex. We're also bobbing up and down through the galactic plane, like a horse on a cosmic carousel, rising above the disk of the galaxy and then falling back through it every 30 million years or so. The sun's journey is long, complex, and utterly beyond our everyday experience. But it's happening right now. We're all travelling together. The Sun's gravity is strong enough to hold Neptune in orbit, despite Neptune being 2.8 billion miles away. This invisible tether extends far beyond even the most distant planets, defining the edge of our solar system. Gravity is strange that way. It has no limit to its range. It gets weaker with distance, but it never completely disappears. Newton described gravity as a force between any two objects with mass, and are proportional to their masses and inversely proportional to the square of the distance between them. Einstein refined this, describing gravity not as a force, but as the curvature of space-time itself. Massive objects like the Sun bend the fabric of space around them, and smaller objects like planets follow the curves, tracing orbits through this warped geometry. Either way you describe it, the result is the same. The Sun's gravity holds the solar system together, whereas it keeps the planets in their orbits, keeps the asteroids in the asteroid belt, keeps the comets in the distant Oort cloud. Even objects trillions of miles away, so far that sunlight is barely distinguishable from starlight, are still gravitationally bound to the Sun. They're still part of the Sun's family, and this gravitational influence extends not just outward, but inward as well. The Sun pulls on the Earth, creating tides, though much weaker than the Moon's tides. It pulls on the gas giants, keeping their massive forms in check. It pulls on every atom, every particle, every speck of dust in the solar system. Gravity is patient. It never stops, never rests. It just keeps pulling, gently but relentlessly, holding everything in place. Solar flares can release as much energy as 1 billion hydrogen bombs exploding simultaneously. These eruptions are among the most powerful events in the solar system, and they happen more often than you might think. During solar maximum, several large flares can occur in a single day. Even during solar minimum, they're not uncommon. A solar flare begins when magnetic field lines in the Sun's atmosphere become twisted and unstable. The tension builds, storing enormous amounts of energy, until finally the field lines snap and reconnect in a violent release. In just a few minutes, temperatures in the flare region can reach tens of millions of degrees. Irradiation across the entire electromagnetic spectrum, from radio waves to X-rays to gamma rays, floods outward into space. If a flare is directed toward Earth, the radiation arrives in about 8 minutes, travelling at the speed of light. It can interfere with radio communications, disrupt GPS signals, and create beautiful auroras at high latitudes. Sometimes, a flare is accompanied by a coronal mass ejection, a massive cloud of plasma and magnetic field that erupts from the Sun's surface. These travel slower, taking days to reach Earth, but when they arrive, they can cause geomagnetic storms that disrupt power grids and damage satellites. The largest solar flare ever recorded occurred in 1859, an event called the Carrington Event. It caused auroras visible as far south as the Caribbean and disrupted telegraph systems worldwide, some of which caught fire. If a flare that powerful occurred today, with our dependence on electronics and power grids, the consequences could be severe. The Sun is gentle most of the time, but it's capable of fury. The Sun is currently in the most stable phase of its life, called the main sequence. It's been in this phase for about 4.6 billion years and will remain there for another 5 billion. This is the long, quiet middle age of a star's life, when fusion proceeds steadily, when the star's size and temperature remain relatively constant, when everything is in balance. The main sequence is defined by equilibrium. The outward pressure from fusion reactions in the core balances the inward pull of gravity. The energy generated in the core equals the energy radiated from the surface. The star neither expands nor contracts. It just shines steadily for billions of years. About 90% of a star's lifetime is spent on the main sequence. It's the default state, the normal condition, the cosmic equivalent of a steady job and a quiet life. Eventually, though, the sun will run out of hydrogen in its core. And when that happens, fusion will slow down and the outward pressure will weaken. Gravity will compress the core, heating it up until a shell of hydrogen around the core begins to fuse. This will cause the sun to expand dramatically, becoming a red giant. It will swell up, perhaps engulfing the inner planets. Earth might survive, but only as a scorched, lifeless rock, orbiting a bloated, dying star. But that's billions of years in the future. For now, the sun is stable. It rises and sets with comforting regularity. It warms the earth, powers the weather, makes plants grow. It's a constant presence, a reliable companion. And in that stability, life has flourished. We exist in the narrow window of the sun's main sequence, in the brief moment when conditions are just right. And for that, we should be grateful. The element helium was discovered in the sun before it was found on Earth. In 1868, during a total solar eclipse, astronomers pointed their spectroscopes at the sun's corona and noticed a strange yellow line in the spectrum, a wavelength of light that didn't match any known element. This was puzzling. Every element produces a unique spectral signature, a fingerprint of light that reveals its presence. But this line was unfamiliar. French astronomer Pierre Janssen and English astronomer Norman Lockyer independently concluded that this must be a new element, the one that existed in the sun but hadn't yet been discovered on Earth. Lockyer named it helium, after Helios, the Greek word for sun. For nearly 3 decades, helium remained a solar mystery, an element we could detect in the sky, but not in our laboratories. Finally, in 1895, Scottish chemist William Ramsay isolated helium on Earth. He extracted it from a uranium ore called cleveite, and when he analysed it with a spectroscope, there it was, the same yellow line that had been seen in the sun's spectrum. The mystery was solved. Helium wasn't just a solar phenomenon. It existed here too, trapped in rocks, floating in the atmosphere in tiny quantities. Now we know that helium is the second most abundant element in the universe, created in the Big Bang and continuously produced in the cores of stars through fusion. It's what gives balloons their lift, what makes voices sound funny when inhaled, what cools superconducting magnets in MRI machines, and we discovered it first not in a laboratory, but in the light of our own star, 93 million miles away. The sun taught us chemistry before we even knew what we were looking for. The sun's powerful magnetic fields can create loops of plasma larger than several Earths. These graceful arches, called prominence loops or coronal loops, are among the most beautiful structures in the solar system. or they glow with the light of superheated plasma, ionized gas trapped and guided by magnetic field lines that arc from one point on the sun's surface to another. Some of these loops are small, barely larger than Earth. Others are enormous, stretching hundreds of thousands of miles into space, tall enough to swallow Jupiter. They can persist for days or weeks, hanging in the corona like glowing bridges before eventually collapsing or erupting. When viewed in ultraviolet or X-ray light, the sun appears as a tangle of these loops, a web of magnetic architecture constantly shifting and reorganizing. The plasma in these loops follows the magnetic field lines like beads on a string. It can't cross the field, only move along it, so the loops act like magnetic highways, channeling material from one part of the sun to another. Sometimes, when loops reconnect or collapse, they can trigger solar flares or coronal mass ejections, releasing the stored magnetic energy in a brilliant flash. These loops are invisible in regular light. You can't see them when you look at the sun with your eyes, only the bright photosphere. But with the right instruments, with telescopes that can see in ultraviolet or X-rays, the sun transforms into something alien and beautiful, a churning, looping, magnetic creature, far more complex and dynamic than the smooth disk we see in the sky. The sun has hidden layers, hidden structures, hidden beauty that only reveals itself when we look in the right way. There's every square meter of the sun's surface shines with the power of about 6,100 watt light bulbs. This is why even a piece of the sun the size of a pinhead would be bright enough to kill a person from over 100 miles away. The sun's surface is radiating energy with an intensity that's almost incomprehensible up close. Imagine standing next to a 100 watt light bulb. You can feel the warmth from a few feet away. Now imagine standing next to 6,000 of them packed into a single square meter. The heat would be overwhelming, unbearable, and that's just 1 square meter. The sun's surface has about 6 trillion square kilometers, each one blazing with that same intensity. Multiply that out, and you get a total power output of about 400 trillion watts. This is why the sun is visible from such vast distances. Pluto, on average, is about 3.7 billion miles from the sun, and even out there in the frozen outer reaches of the solar system, the sun is still the brightest object in the sky. It's dimmer than it appears from Earth, of course, about as bright as a full moon looks to us, but it's still clearly visible, still the dominant light source. From Earth, we're shielded from most of this intensity by 93 million miles of empty space. The light spreads out, dilutes, weakens according to the inverse square law. By the time it reaches us, it's gentle enough to warm our skin without burning it, bright enough to see by but not blinding. We exist in just the right spot, at just the right distance, where the sun's intensity is perfect for life. A little closer and we'd roast, a little farther and we'd freeze. But here, 93 million miles away, it's just right. The sun produces neutrinos, ghostly particles that pass through matter almost without interaction. Trillions of solar neutrinos are passing through your body right now, mostly without touching a single atom. They're streaming out from the sun's core, where they're created as byproducts of nuclear fusion, and they travel outward at nearly the speed of light. Unlike photons, which bounce around inside the sun for thousands of years before escaping, neutrinos barely interact with anything. They pass straight through the sun's interior as if it weren't there. They pass through Earth just as easily, through the rock, through the oceans, through buildings, through you. Only very rarely, perhaps once in 1,000,000,000,000 encounters, or will a neutrino actually collide with an atom. This makes neutrinos incredibly difficult to detect. To catch them, scientists build enormous detectors deep underground, shielded from other particles. These detectors contain thousands of tons of ultra-pure water or other materials, and they wait. They wait for the rare moment when a neutrino happens to strike an atom, producing a tiny flash of light. From these rare flashes, scientists can learn about what's happening in the sun's core. Right now, in real time. This is remarkable when you think about it. The light we see from the sun is ancient. It took thousands of years to escape the sun's interior, but neutrinos are fresh. They tell us what's happening in the core this very moment. They're messengers from the heart of the sun, carrying news that nothing else can deliver. And they're passing through you right now as you read this. Invisible, intangible, ghostly travelers from the furnace at the center of our solar system. The ancient Greek philosopher Anaxagoras was exiled for suggesting the sun was a giant hot rock rather than a deity. In the 5th century BCE, this was considered dangerous heresy. The sun was sacred, divine, a god that crossed the sky each day in a golden chariot. To suggest it was just a physical object subject to natural laws was to challenge the very foundation of religious belief. Anaxagoras proposed that the sun was a mass of fiery metal, perhaps as large as the Peloponnese Peninsula. He was wrong about the details, of course. The sun is much, much larger than that, and it's not made of metal. But he was remarkably close to the truth in spirit. The sun is a physical object, governed by natural processes, not by divine will. It shines because of nuclear fusion, not because a god commands it to. This idea was so controversial that Anaxagoras was charged with impiety and forced to leave Athens. His crime was thinking scientifically about something that was supposed to remain sacred and mysterious. He dared to apply reason and observation to the heavens, and for that he was punished. But his ideas survived. They influenced later philosophers, including Aristotle and the atomists. Slowly, over centuries, the scientific understanding of the sun emerged. We learned that it's not a god, not a chariot, not a mass of fiery metal. We learnt that it's a star, a ball of plasma, and powered by fusion. And yet, in a way, this knowledge doesn't diminish the sun. If anything, it makes it more awe-inspiring. The sun doesn't need to be a deity to be magnificent. The truth, the physics, the fusion, the billions of years of history is wonder enough. The sun's core is so dense that a teaspoon of its material would weigh about 5 pounds on Earth. This is over 150 times denser than water, despite being entirely gaseous. It seems contradictory, doesn't it? We think of gas as light, diffuse, barely there. But at the center of the sun, under the crushing weight of all the layers above, matter is compressed into a state unlike anything we experience on Earth. The pressure at the core is about 250 billion times Earth's atmospheric pressure at sea level. Under these conditions, atoms are stripped of their electrons, packed together so tightly that the normal rules of matter seem to bend. And yet, it's still technically a gas, a plasma, to be precise, because the particles are moving freely, not locked in a solid or liquid structure. It's just an incredibly dense, incredibly hot, incredibly compressed gas. This density is essential for fusion. For hydrogen nuclei to fuse into helium, they need to collide with tremendous force. And for that to happen, they need to be packed tightly together and heated to millions of degrees. The Sun's core provides exactly those conditions. The gravity of all the Sun's mass crushes the core into this dense, hot state, and fusion begins. As you move outward from the core, the density decreases. The radiative zone is less dense than the core, the convective zone is less dense still, and the photosphere, the visible surface, is about 1,000 times less dense than Earth's air at sea level. It's so tenuous you could almost call it a vacuum. But at the center, in that tiny core where all the Sun's energy is generated, matter is compressed into a state of almost unimaginable density. 5 pounds per teaspoon, heavy as a stone, but made entirely of gas. The Sun creates a bubble in space called the heliosphere that extends far beyond Pluto. This magnetic bubble shields our solar system from most galactic cosmic rays, making space near Earth safer. Without it, radiation from deep space would penetrate much deeper into the solar system, potentially stripping away planetary atmospheres and making life on Earth far more difficult. The heliosphere is created by the solar wind, the constant stream of charged particles flowing outward from the Sun in all directions. This wind travels at hundreds of miles per second, carrying the Sun's magnetic field with it. It blows outward, pushing against the interstellar medium, the thin gas and dust that fills the space between stars, and at a certain distance, roughly 120 astronomical units from the Sun, about 11 billion miles, the solar wind slows down and forms a boundary called the heliopause. This is the edge of the solar system in a very real sense. Beyond the heliopause, the Sun's influence fades. The solar wind gives way to the interstellar medium. The magnetic field carried from the Sun weakens and is replaced by the galactic magnetic field. In 2012, Voyager 1 became the first human-made object to cross the heliopause, entering interstellar space after 35 years of travel. The heliosphere isn't a perfect sphere. It's shaped more like a comet, with a long tail streaming behind the Sun as it moves through the galaxy. The side facing the Sun's direction of motion is compressed, while the opposite side stretches out into a long trailing structure called the heliotail. The whole thing shifts and changes as the solar wind varies in strength as the Sun goes through its activity cycles. We live inside this bubble, protected by the Sun's magnetic embrace, mostly unaware of the cosmic radiation that's being deflected away from us every moment of every day. In about 5 billion years, the Sun will expand into a red giant star, possibly engulfing Mercury and Venus. Earth might survive, but only as a scorched, lifeless rock orbiting a vastly larger, cooler star. This is the eventual fate of all stars like the Sun, a dramatic transformation that marks the beginning of the end. When the sun exhausts the hydrogen in its core, fusion will slow down. The outward pressure from fusion will weaken, and gravity will compress the core further, heating it up. This will cause a shell of hydrogen around the core to begin fusing, and the energy from this shell fusion will cause the outer layers of the sun to expand dramatically. The sun will swell up, growing hundreds of times larger than it is now, becoming a red giant. The surface temperature will drop, making the sun appear redder, but the total energy output will increase. The sun will be brighter, more luminous, even as its surface cools, and as it expands it will swallow the inner planets. Mercury will almost certainly be consumed, Venus probably as well. Earth's fate is uncertain. Some models suggest it will be engulfed. Others suggest it will survive, its orbit pushed outward as the sun loses mass. But either way, Earth will be uninhabitable. The oceans will boil away. The atmosphere will be stripped off. The surface will be baked by the intense heat of the nearby red giant. This sounds grim, but it's billions of years away. For now, the sun is stable, predictable, life-sustaining, and even in its death, the sun will create something beautiful. When it sheds its outer layers, it will form a planetary nebula, a glowing shell of gas expanding into space, illuminated by the hot core that remains. This core will become a white dwarf, slowly cooling over trillions of years. The sun's death will be slow, dramatic, and visible across light years. A final performance before the curtain falls. The sun produces about 1,000 times more energy than all of humanity uses in a year, every single second. This power comes entirely from converting mass into energy. According to Einstein's famous equation, E equals mc squared. 4 hydrogen nuclei fuse into one helium nucleus, and in the process, a tiny amount of mass disappears. That mass doesn't really disappear, of course. It transforms. It becomes energy, pure energy, in the form of photons and neutrinos. The amount of mass converted is incredibly small. Only about 0.7% of the hydrogen's mass is turned into energy during fusion. But because the speed of light squared, c squared, is such an enormous number, even a tiny amount of mass yields a tremendous amount of energy. 1 kilogram of matter fully converted to energy, and would release about 90 trillion joules, equivalent to several large nuclear bombs. The sun converts about 600 million tons of hydrogen into helium every second, losing about 4 million tons as energy. 4 million tons sounds like a lot, and it is. But spread across the sun's entire surface, radiated out into space in all directions, it dilutes into the gentle warmth we feel on Earth, the light that makes plants grow, the energy that powers the wind and the waves. Einstein's equation united matter and energy, showing they're 2 forms of the same thing. The sun demonstrates this unity every second. Mass flows in, hydrogen nuclei colliding, fusing. Energy flows out, light, heat, neutrinos, solar wind. The sun is a converter, a transformer, turning matter into the radiation that fills the solar system. And it's been doing this for billions of years, with enough fuel remaining to do it for billions more. Mass becomes energy, energy becomes life, and we, made of atoms forged in ancient stars, stand in the light of our own star and try to understand. The sun's visible surface, called the photosphere, is only about 300 miles thick. This thin layer is all we can see, hiding the vast, dense interior beneath. It's strange to think about. The Sun's radius is about 432,000 miles, but the part we actually see with our eyes, the luminous surface, is just a thin shell, less than 0.1% of the radius. Below the photosphere is the convective zone, where hot plasma churns and bubbles upward. Below that is the radiative zone, where energy slowly diffuses outward through countless absorption and emission events. And below that is the core, where fusion happens. All of this is hidden, invisible, inferred only through mathematics and indirect observations. Above the photosphere is the chromosphere, a thin layer of hot gas that appears red during eclipses, and above that is the corona, the Sun's outer atmosphere, which extends millions of miles into space. So the photosphere is really just a boundary, a transition zone between the dense interior and the tenuous outer atmosphere. When we look at the Sun, we're seeing light emitted from this thin shell, photons that have finally escaped after their long journey from the core. The photosphere is where the Sun becomes transparent, where photons can finally travel freely without being absorbed and re-emitted. It's the surface only in the sense that it's where we stop being able to see inward. Below it, the Sun is opaque. Above it, the Sun is mostly transparent, and in that narrow zone, 300 miles thick, the Sun's light is born into the visible world. It's a reminder that what we see is often just the surface, just the outer layer. The real complexity, the real dynamics, the real story, it's always deeper than what's visible. The Sun, like so many things, hides most of itself from view. These solar wind particles travel at speeds of about 250 to 500 miles per second. This constant stream of charged particles takes about 3 to 4 days to reach Earth. It's a wind unlike anything we experience on our planet, not air molecules pushed by pressure differences, but a plasma of electrons and protons flowing outward from the Sun's corona, accelerated by heat and magnetic forces to supersonic speeds. The solar wind is always there, always flowing, like a cosmic river. During quiet times, it's relatively gentle, just a steady stream of particles washing over the planets. But during solar storms, when coronal mass ejections erupt from the Sun's surface, the solar wind becomes a gale. These bursts of dense plasma can travel even faster, sometimes reaching Earth in as little as 15 to 18 hours. When solar wind particles reach Earth, most are deflected by our planet's magnetic field. They slide around us, diverted by invisible magnetic lines, and flowing past like water around a stone in a stream. But some particles get funneled toward the magnetic poles, where they collide with atoms in the upper atmosphere. These collisions release energy as light, creating the auroras, the northern and southern lights. Green, red, purple curtains of light dancing across the polar skies, a visible reminder that we live in the Sun's atmosphere, even here, 93 million miles away. The solar wind eventually reaches the edge of the heliosphere, where it slows and mingles with the interstellar medium. But for the inner planets, for Earth and Mars and Venus, the solar wind is a constant presence, a reminder that the space between the planets is not truly empty. It's filled with the Sun's breath, carrying particles and magnetic fields outward into the void. The Sun has been observed continuously from space since 1996, giving us an unprecedented view of its behaviour. These satellites like SOHO, the Solar and Heliospheric Observatory, have revolutionised our understanding of solar dynamics and space weather. Before these satellites, we could only observe the Sun from Earth's surface, and only during the day, and only when clouds didn't obscure the view. But SOHO sits at a special point in space called the L1 Lagrange point, about 1 million miles from Earth, directly between Earth and the Sun. From there, it has an uninterrupted view of our star 24 hours a day, 365 days a year. It watches the Sun in multiple wavelengths, capturing images in ultraviolet and visible light, measuring the solar wind, tracking coronal mass ejections as they erupt and travel toward Earth. This continuous observation has taught us things we never could have learned from ground-based telescopes. We've seen how the Sun's corona constantly changes, how prominences rise and fall, how the magnetic field reorganizes itself. We've learned to predict space weather with greater accuracy, giving warning when solar storms might disrupt satellites or power grids. We've discovered thousands of comets by watching them pass near the Sun, their icy surfaces vaporizing in the intense heat. And we've simply watched the Sun, day after day, year after year, building up a record of its behavior that spans decades now. We've seen it go through multiple solar cycles from minimum to maximum and back again. We've seen quiet periods and active periods, flares and eruptions and calm stretches when the Sun's face is smooth and unmarked. The Sun is no longer a mystery that only reveals itself during the day. It's a constant companion, watched and studied and understood in ways that would have seemed impossible just a few generations ago. The Sun's magnetic field is about twice as strong as Earth's at the surface, but far more complex. While Earth's field resembles a simple bar magnet, with clean north and south poles, the Sun's field constantly twists, tangles, and reconfigures itself. It's not a single, stable field, but a chaotic, ever-changing web of magnetic lines threading through the Sun's atmosphere. This complexity arises from the Sun's nature as a plasma sphere. Earth is solid, with a liquid core that generates a relatively simple magnetic field through convection and rotation. But the Sun is entirely fluid, and different parts rotate at different speeds. The equator spins faster than the poles, and this differential rotation stretches and twists the magnetic field lines like rubber bands. These twisted field lines store enormous amounts of energy. When they become too tangled, too stressed, they can snap and reconnect, releasing that energy in solar flares and coronal mass ejections. The magnetic field also creates sunspots, regions where strong fields suppress convection and cool the surface. It shapes the corona, guiding plasma into graceful loops and arches. It accelerates the solar wind, channeling particles outward along field lines. Every 11 years, as we've discussed, the Sun's magnetic field flips. But even between these flips, the field is never still. It's always moving, always reconfiguring, always responding to the churning convection and rotation deep inside the Sun. If you could see magnetic field lines the way you see light, the Sun would look like a living thing, meet a tangle of glowing threads constantly weaving and unweaving themselves, pulsing with energy, never the same from one moment to the next. The pressure at the Sun's core is about 250 billion times Earth's atmospheric pressure at sea level. Under these extreme conditions, the normal rules of physics take on strange and beautiful forms. Matter behaves in ways that seem impossible by our everyday experience, yet they're essential for the Sun's existence. At sea level on Earth, the atmospheric pressure is about 14.7 pounds per square inch. This is the weight of all the air above you pressing down. It's enough to crush an empty container, to hold water in a straw, to make your ears pop when you change elevation quickly. But it's gentle compared to what happens inside the Sun. At the core, the pressure is so immense that hydrogen nuclei, which would normally repel each other due to their positive electric charges, are forced close enough to fuse. The temperature helps too. Of course, at 27 million degrees, the nuclei are moving fast enough to overcome some of their electromagnetic repulsion. But pressure is just as important. It packs the nuclei together, increases the likelihood of collisions, creates the conditions where fusion becomes inevitable. This pressure also prevents the Sun from collapsing under its own gravity. The core is incredibly hot, and hot gas expands, creating an outward pressure that balances the inward pull of gravity. This balance, called hydrostatic equilibrium, is what keeps the Sun stable. If fusion suddenly stopped, the pressure would drop, and gravity would compress the core further. If fusion suddenly increased, the pressure would rise and the Sun would expand, but they balance each other almost perfectly, maintaining the Sun in a stable state for billions of years. It's a delicate dance, really. Pressure and gravity, fusion and collapse, expansion and contraction, all in perfect balance. At pressures we can barely imagine, in a place we'll never visit. The Sun is currently passing through a region of space called the Local Interstellar Cloud. This wispy cloud of gas is just one of many the Sun will traverse during its long journey around the galaxy. The Local Interstellar Cloud isn't like the clouds we see in Earth's sky. It's incredibly tenuous, more like a very, very faint haze. Its density is only about 0.3 atoms per cubic centimetre, compared to about 10 to the power of 19 molecules per cubic centimetre in Earth's atmosphere at sea level. And yet, sparse as it is, this cloud has properties. It has a temperature, about 6,000 degrees Kelvin, roughly the same as the Sun's surface. It has a magnetic field. It has a slight pressure, a slight density. And the Sun, as it travels through the galaxy, passes through regions like this, sometimes entering denser clouds, sometimes emerging into the near-perfect vacuum of interstellar space, where these clouds can affect the heliosphere, the bubble of solar wind that surrounds our solar system. When the Sun enters a denser region, the external pressure increases and the heliosphere can shrink slightly. When it emerges into a less dense region, the heliosphere expands. These changes happen over thousands or millions of years, so slowly that they're barely noticeable on human timescales. The Sun has been in the Local Interstellar Cloud for somewhere between 44,000 and 150,000 years, depending on which estimates you trust. Eventually it will emerge from this cloud and enter another region of interstellar space. the journey continues through different neighborhoods of the galaxy, through clouds and voids, through regions thick with gas and regions almost empty. The sun is a traveller carrying us along, and the galaxy is vast enough that the journey never truly ends. Ancient Chinese astronomers kept detailed records of sunspots as early as 800 BCE. They noticed these dark spots appearing and disappearing, documenting solar activity millennia before the telescope. To the naked eye, especially when the sun is low on the horizon and its light is dimmed by atmospheric haze, large sunspots can sometimes be visible as small, dark marks on the sun's disk. The Chinese treated these observations with the same careful attention they gave to other celestial phenomena, lunar eclipses, comets, planetary movements. They recorded when sunspots appeared, yet how long they lasted, sometimes even their approximate sizes. They didn't understand what sunspots were, of course. They couldn't have known about magnetic fields or plasma or convection. But they knew the sun wasn't perfectly uniform, that it changed over time, that it had features worth noting and remembering. In Europe, the prevailing view for much longer was that the heavens were perfect and unchanging. The sun, the moon, the stars, these were divine, eternal, unmarred by imperfection. When Galileo observed sunspots through his telescope in 1610, it was controversial. Some argued that the spots weren't on the sun itself, but were small planets passing in front of it. The idea that the sun had blemishes was almost heretical. But the Chinese astronomers, unencumbered by these philosophical constraints, simply recorded what they saw. Dark spots on the sun, appearing, persisting for days or weeks, then fading. It's a reminder that science doesn't require perfect instruments or complete theories. Sometimes it just requires careful observation, honest record keeping, and the humility to accept what you see, even if you don't fully understand it. The ancient Chinese didn't know why sunspots existed, but they knew they were real, and their records, preserved for thousands of years, are still valuable to modern solar scientists studying long-term solar cycles. The sun's energy output varies by only about 0.1% over its 11-year activity cycle. This remarkable stability has allowed complex life to flourish on Earth for billions of years. Imagine if the sun were unpredictable, if it dimmed by 10% or brightened by 20% on a whim. Earth's climate would swing wildly between freezing and scorching. Oceans would freeze solid, then boil away. Life would struggle to adapt, and complex ecosystems might never develop. But the sun is steady. Yes, it goes through cycles. Yes, it has sunspots and flares and coronal mass ejections. Yes, its magnetic field flips every 11 years, but through all of this activity, its total energy output barely changes. The variations are there, measurable by precise instruments, but they're tiny. Earth's climate system can absorb these fluctuations without catastrophic changes. This stability is a consequence of the sun's size and the nature of fusion. Large stars are more stable than small ones because their gravity provides stronger regulation. If fusion speeds up slightly, the core expands and cools, slowing fusion back down. If fusion slows, the core contracts and heats up, speeding fusion back up. It's a self-regulating system, a cosmic thermostat that keeps the sun shining at a nearly constant brightness. This is one reason why we exist. The sun's stability provided a predictable energy source for billions of years, allowing evolution to proceed, allowing ecosystems to develop, allowing life to experiment with increasing complexity. A variable star would be a harsh parent, subjecting its planets to constant climate upheaval, but the sun is gentle, patient, reliable. It has been for 4.6 billion years, and it will continue to be for billions more. In that stability, life found a foothold, and here we are, the result of that long, patient shining. The sun generates its magnetic field through a process called the solar dynamo. The complex interaction of rotation, convection, and plasma creates magnetic fields that tangle and twist in hypnotic patterns. It's not fully understood, even today. The details are still being worked out, still being studied through computer simulations and observations. Here's what we think happens. The sun's convective zone is filled with churning plasma, ionized gas that conducts electricity. As this plasma moves, it carries magnetic fields with it. The rotation of the sun twists these fields, stretching them in the direction of rotation. The differential rotation, the fact that the equator spins faster than the poles, stretches and winds the field lines even more, creating complex, tangled structures. At some point, these tangled fields become unstable. They rise toward the surface, creating sunspots where they break through. They twist and reconnect, releasing energy in flares. And eventually, after about 11 years of this twisting and tangling, the field becomes so complex that it flips, reorganizing itself into a new configuration with reversed polarity. Then the process begins again. It's a continuous cycle of creation and destruction, order and chaos. The solar dynamo is always running, always generating new magnetic fields, always twisting them into new shapes, and from this churning magnetic complexity emerges. The sun's magnetic field isn't a static thing, imposed from outside. It's generated from within, by the sun's own motion, by the interaction of rotation and convection. The sun creates its own magnetic personality, and that personality is always changing, always evolving, always surprising us with new behaviors and patterns. The sun experiences seasons of activity, with solar maximums and minimums occurring in roughly 11-year cycles. During solar maximum, the sun can produce dozens of sunspots, while during minimum, the days can pass with none at all. This cycle is one of the most obvious signs of the sun's changing magnetic field, a rhythm that's been beating for as long as the sun has existed. Right now, as of early 2025, we're in solar cycle 25, which began in December 2019. This sun is climbing towards solar maximum, expected around 2025 or 2026. Sunspots are becoming more common. Solar flares are increasing in frequency. The corona is more active, more structured, more visibly complex, and then, year after maximum, the activity will gradually decline. Sunspots will become rarer, flares will decrease, the sun's face will become smoother, quieter, as we slide toward the next solar minimum. These cycles aren't perfectly regular. Some maximums are strong, with hundreds of sunspots visible over the course of a year. Others are weak, with only modest activity. The 11-year period is an average. Some cycles are shorter, some longer. And there are hints of longer cycles too. Patterns that play out over centuries, like the Maunder minimum in the 1600s when sunspots almost completely disappeared for decades. But the basic rhythm persists. Maximum, minimum, maximum, minimum. The sun breathes in a sense. It inhales magnetic complexity and exhales it. It builds up energy and releases it. It's never truly still, never truly uniform. Even during solar minimum, when the sun appears calm and featureless, the dynamo is still running beneath the surface, twisting field lines. He is building toward the next maximum. The cycle continues, as it has for billions of years and will for billions more. The sun's gravitational pull creates tides on Earth, though they're much weaker than the moon's tides. Solar tides are about 46% as strong as lunar tides, and the two work together to create spring and neap tides. When the sun and moon are aligned during new moons and full moons, their tidal forces add together, creating higher high tides and lower low tides. These are called spring tides, though they have nothing to do with the season. When the sun and moon are at right angles, during the first and third quarter moons, their tidal forces partially cancel out, creating more moderate tides called neap tides. The difference isn't huge, but it's noticeable to anyone who spends time near the ocean. Fishermen know, sailors know. People who live by the sea can feel the rhythm, the monthly cycle of tides swelling and shrinking. The sun's tidal force is weaker than the moon's because although the sun is vastly more massive, it's also vastly farther away. Tidal forces depend on the gradient of gravity, how quickly gravity changes from one side of an object to the other. The moon, being much closer, creates a steeper gradient despite its smaller mass. But the sun still contributes, still pulls on Earth's oceans, still influences the rise and fall of the tides. It's another subtle way the sun shapes our world, yet not just through light and heat, but through gravity. It holds us in orbit, creates tides, keeps the solar system organized and stable. The sun's influence is everywhere, even in places you might not expect, even in the rhythm of the ocean, the pattern of waves on a shore, the timing of high tide. The sun is always there, always pulling, always present. The sun will eventually run out of hydrogen in its core and begin fusing helium into heavier elements. This transition will mark the beginning of the end of the sun's life as we know it. For billions of years, the sun has been fusing hydrogen into helium, 4 protons combining to make one helium nucleus, releasing energy in the process. But fusion produces helium ash that accumulates in the core, and slowly, over billions of years, the hydrogen fuel depletes. When the core finally runs out of hydrogen, fusion will stop there. The core, no longer supported by the outward pressure of fusion, will begin to contract under its own gravity. As it contracts, it will heat up, and eventually it will get hot enough, about 100 million degrees, for helium fusion to begin. 3 helium nuclei will fuse into carbon, releasing energy in what's called the triple alpha process. But helium fusion is different from hydrogen fusion. It produces more energy per reaction, but burns through fuel much faster. The sun will spend only about 100 million years fusing helium, compared to the 10 billion years it spends fusing hydrogen. It's a brief, intense phase, like a final sprint after a long, steady marathon. And during this phase, the sun will change dramatically. It will expand into a red giant, possibly swallowing the inner planets. It will brighten considerably, shining thousands of times more luminous than it does now. And then, when the helium is exhausted, the sun won't be massive enough to fuse carbon into heavier elements. It will simply shed its outer layers, creating a planetary nebula, and leave behind a white dwarf core that will slowly cool over trillions of years. This is the fate of all stars like the sun. Not a violent supernova, but a gradual dimming, a slow fade into darkness. In a way, it's a gentle death, but it's billions of years away. For now, the sun is middle-aged, stable, full of hydrogen fuel. For now, we have time. The temperature difference between the sun's core and its surface spans about 27 million degrees. This represents one of the most extreme thermal gradients anywhere in the solar system. At the very center, temperatures reach 27 million degrees Fahrenheit. At the surface, they're only about 10,000 degrees. That's a drop of 27 million degrees over a distance of about 432,000 miles. This gradient drives everything that happens inside the sun. Heat flows from hot to cold, from the core outward. In the radiative zone, energy moves as photons, bouncing from atom to atom in a slow random walk. In the convective zone, hot plasma rises, cools, and sinks back down in vast churning cells. This sun is a heat engine, and this temperature difference is what powers it. On Earth, we have temperature gradients too, of course. The difference between a summer day and a winter night might be 100 degrees. The difference between the equator and the poles might be 150 degrees. But these are tiny compared to the sun's internal gradient. The sun contains extremes that we can barely imagine. Extremes that would vaporize any material instantly. Extremes that exist only in the cores of stars and in the hearts of nuclear explosions. And yet, from those extremes the sun produces the gentle warmth we feel on our skin. The 27 million degrees at the core becomes 10,000 degrees at the surface, becomes the comfortable warmth of a sunny afternoon. The sun is a transformer, not just of matter into energy, but of extreme heat into livable temperatures. It takes the inferno at its core and spreads it out, dilutes it, moderates it, until by the time it reaches us 93 million miles away, it's just right. The sun's visible light takes about 2 seconds to travel from the sun to the moon. This means when we see a full moon, we're seeing sunlight that bounced off the moon as recently as 2 seconds ago. The moon is about 240,000 miles from Earth on average, and light travels at 186,000 miles per second, so the light takes a bit more than a second to travel from the moon to our eyes. But before that, it had to travel from the sun to the moon, about 93 million miles, which takes roughly 8 minutes and 20 seconds. So the total journey, sun to moon to Earth, takes about 8 minutes and 22 seconds. The sunlight illuminating the moon during a full moon left the sun just over 8 minutes ago, bounced off the lunar surface about 2 seconds ago, and is reaching your eyes right now. It's strange to think about moonlight this way. We often speak of moonlight as if it's something the moon produces, as if the moon glows on its own. But of course it doesn't. The moon is just a rock, a cold, airless sphere of stone reflecting sunlight. All moonlight is second-hand sunshine, light that's already travelled 93 million miles and is now making a brief detour via the moon before continuing onto Earth. And because the moon's surface is rough and grey, it doesn't reflect light very efficiently. Only about 12% of the sunlight that hits the moon is reflected back. The rest is absorbed, heating the lunar surface. So moonlight is not only delayed sunlight, but also dimmed sunlight. It's a pale, ghostly version of the original. And yet it's enough to cast shadows, enough to light a path, enough to inspire poets and lovers and dreamers for thousands of years. Second-hand sunshine, and travelling across the void, bouncing off a dead world, and arriving just in time to illuminate the night. The sun creates heavy elements inside its core through nuclear fusion, though only up to carbon and oxygen. Elements heavier than these require even more extreme conditions found only in supernova explosions. This is one of the fundamental limitations of stellar evolution. The sun isn't massive enough to fuse elements heavier than carbon and oxygen. When the sun eventually fuses helium into carbon, some of that carbon will fuse into oxygen, but that's where it stops. To fuse carbon into heavier elements like neon, magnesium, silicon, or iron, you need higher temperatures and pressures. You need a more massive star. Stars that are 8, 10, 20 times the mass of the sun can fuse progressively heavier elements, building up an onion-like structure with iron at the core. But even those massive stars can't fuse iron into anything heavier. Iron is the end of the line for fusion. Fusing iron doesn't release energy, it absorbs energy. So when a massive star's core fills up with iron, fusion stops, the core collapses, and the star explodes in a supernova. In that explosion, in the unimaginable heat and pressure of the collapsing core and rebounding shock wave, elements heavier than iron are created. Gold, platinum, uranium, all the heavy elements in the universe were made in supernovas or in the collisions of neutron stars. The sun will never explode. It will never create gold or lead or uranium, but it will create carbon and oxygen, and when it dies, it will scatter those elements into space, and perhaps, billions of years from now, those atoms will be incorporated into new stars, new planets, maybe even new life. The sun is part of a cycle, a cosmic recycling program where stars create elements, die, and seed space with the raw materials for future generations. It's beautiful in a way. Even in death, stars are generous. The sun's corona, visible during total solar eclipses, extends millions of miles into space. This wispy, pearlescent atmosphere has captivated eclipse observers for millennia. During an eclipse, when the moon blocks the bright photosphere, the corona suddenly becomes visible, a delicate halo of light surrounding the darkened sun, with streamers and plumes extending outward in graceful curves. The corona is incredibly hot, as we've mentioned, millions of degrees, and far hotter than the surface below it, and it's incredibly tenuous, with a density about 1 trillion times less than Earth's atmosphere at sea level. If you could somehow stand in the corona, you'd barely feel anything. Individual atoms are moving at tremendous speeds, carrying enormous energy, but there are so few of them that the total heat transfer would be minimal. The corona's structure reflects the sun's magnetic field. Streamers follow magnetic field lines, creating the characteristic shape we see during eclipses. Near the poles, the field lines are often open, allowing plasma to escape into space as the fast solar wind. Near the equator, the field lines form loops and arches, trapping plasma and creating the helmet streamers that give the corona its crown-like appearance. For thousands of years, people witnessed solar eclipses and saw the corona without understanding what it was. Some thought it was the moon's atmosphere. Some thought it was a halo of divine light. But now we know it's the sun's outer atmosphere, a region where the normal rules seem to break down, where temperatures rise instead of fall, where gravity barely holds on to the tenuous plasma. The corona is a boundary region, a transition between the sun and interplanetary space. And for a few precious minutes during a total solar eclipse, we can see it with our own eyes, a reminder that the sun is more than just a bright disk in the sky. The sun loses about 1.5 million tons of material per second through the solar wind. Despite this constant outpouring, the sun has enough mass to sustain this loss for trillions of years. It sounds like an enormous amount, and it is, but remember, the sun is unimaginably massive, about 2 times 10 to the 31st power kilograms. Losing 1.5 million tons per second is like a drop of water evaporating from the ocean. It's measurable, but barely significant. The solar wind is made up of electrons and protons mostly, streaming away from the corona at hundreds of miles per second. Some of this comes from the slow solar wind, which flows at about 250 miles per second. Some comes from the fast solar wind, which can reach 500 miles per second or more. Together they create a constant breeze blowing outward through the solar system. This outflow has been happening for billions of years. Throughout Earth's history, throughout the formation and evolution of the planets, the sun has been losing mass through the solar wind, and it will continue for billions more years. Eventually, when the sun becomes a red giant and then sheds its outer layers to form a planetary nebula, the mass loss will increase dramatically. But even then, even shedding a significant fraction of its mass, the sun won't disappear. It will leave behind a white dwarf, a dense remnant containing about 60% of the sun's current mass, compressed into an object about the size of Earth. So, yes, this sun is slowly evaporating, but it's a process so gradual that, for all practical purposes, the sun is eternal, at least on human timescales, at least for the foreseeable future. The sun will outlast our civilization, our species, possibly even our planet. It will keep shining, keep losing mass, keep blowing its wind across the solar system, long after we're gone. The sun's rotation has slowed down over its lifetime due to the magnetic braking effect. Like a spinning figure skater extending their arms, the sun's magnetic field interacts with the solar wind to gradually slow its spin. When the sun was young, just a few million years old, it rotated much faster, perhaps once every few days. But as the solar wind carried away angular momentum along magnetic field lines, the rotation slowed. Now the sun's equator rotates once every 25 days or so. It's lost most of its original spin, and this process continues, very slowly, even today. Every year, the sun rotates a tiny bit slower. Over billions of years this adds up. By the time the Sun becomes a white dwarf, it might rotate only once every few weeks or even months. This magnetic braking also affects other stars, especially young ones. When astronomers observe clusters of stars all born at the same time, they can measure their rotation rates and see this effect in action. The younger stars spin rapidly, older stars spin more slowly, and the rate of slowdown depends on the strength of the magnetic field and the solar wind. Stars with stronger fields and more intense winds slow down faster. It's a reminder that stars aren't static. They evolve, not just in their internal structure and energy output, but in their rotation, their magnetic fields, their activity levels. The Sun today is different from the Sun of 4 billion years ago, and different from the Sun that will exist 4 billion years in the future. It's changing, and constantly, just very slowly. Slowly enough that we don't notice in a human lifetime, but quickly enough to matter over the age of the solar system. The Sun's light pressure is strong enough to push on objects, creating comet tails that always point away from it. This gentle but persistent force has even been harnessed to propel spacecraft using solar sails. Light carries momentum. Individual photons have no mass, but they have energy. And when they strike an object and are absorbed or reflected, they transfer a tiny amount of momentum. For most objects, this force is negligible, overwhelmed by gravity and other forces. But for very light objects spread over a large area, like dust particles or thin reflective sails, light pressure becomes significant. This is why comet tails always point away from the Sun, regardless of which direction the comet is moving. As a comet approaches the Sun, its icy surface heats up and vaporizes, releasing dust and gas. The gas is pushed away by the solar wind, and the dust is pushed away by light pressure. The result is a long tail streaming away from the Sun, sometimes millions of miles long. Solar sails work on the same principle. A large, thin, reflective sheet, made of something like a luminized mylar, catches sunlight. Photons bounce off the sail, transferring momentum, and the spacecraft slowly accelerates. The force is tiny, but it's constant, and over time, it can build up significant speed. Unlike rockets, which carry fuel and eventually run out, solar sails can accelerate as long as there's sunlight. They're limited only by the strength of the sail and the patience of the mission planners. It's a beautiful concept, really. Using light itself as a propellant, riding the photons streaming out from the Sun, surfing on sunshine, propelled by the same force that pushes comet tails across the sky. The Sun gives us light, heat, energy, and now, potentially motion. A gentle push, continuous and free, carrying us across the solar system. The Sun experiences earthquakes called solar quakes after major flares. These ripples travel across the Sun's surface at speeds of up to 250,000 miles per hour. Imagine the surface of a pond after you drop a stone. Ripples spreading outward in concentric circles. Now imagine those ripples moving at 250,000 miles per hour, carrying the energy of a large solar flare, disturbing the Sun's photosphere as they pass. Solar quakes were first observed in 1996 during a powerful solar flare. Scientists noticed ripples spreading outward from the flare site, travelling across the Sun's surface like seismic waves on Earth. But unlike earthquakes, which are caused by tectonic plates shifting, solar quakes are caused by sudden releases of magnetic energy. When a flare erupts, it deposits enormous amounts of energy into the photosphere and chromosphere, creating a shock wave that propagates outward. These quakes can have wavelengths of tens of thousands of miles and amplitudes of hundreds of miles. They shake the sun's surface, disturbing the delicate balance of temperature and pressure, sending waves rippling through the plasma. And then, within an hour or so, they dissipate, absorbed by the sun's churning convection and turbulent atmosphere. The sun is not solid, so these quakes don't behave exactly like earthquakes on Earth. But the analogy is close enough. The sun shakes. It trembles in response to violent events. It rings like a bell after being struck, vibrating at frequencies we can measure with sensitive instruments. Even the sun, vast and powerful as it is, can be disturbed. Even the sun feels the impact of its own fury. The sun is about 25,000 light-years from the center of the Milky Way galaxy. We orbit in a relatively quiet suburban neighborhood of the galaxy, far from the chaotic central regions. The galactic center is a crowded, violent place. Stars are packed closely together. Massive black holes lurk in the darkness. Supernovas explode with regularity. Intense radiation floods the region. If Earth were there, life as we know it would be impossible. But out here, 25,000 light-years away, things are calmer. Stars are spread out. The night sky is relatively dark. The radiation environment is gentler. We're far enough from the center to avoid most of the chaos, but not so far out that we're in the sparse, lonely outer reaches of the galaxy. We're in what astronomers sometimes call the galactic habitable zone, a region where conditions are stable enough for life to develop. The sun orbits the galactic center at a speed of about 514,000 miles per hour, completing one orbit every 225 to 250 million years. Along the way, it passes through spiral arms, regions of higher stellar density where star formation is active and supernova rates are higher. And then it emerges into the quieter regions between the arms, where the radiation environment is calmer. Right now, we're between spiral arms, in a relatively quiet stretch of the galaxy. This might not be a coincidence. Some scientists have suggested that life on Earth has flourished in part because we spend most of our time in these quieter regions, away from the radiation and gravitational disturbances of the spiral arms. It's speculative, but intriguing. Maybe we're here. We're thinking these thoughts, in part because the sun chose a safe, quiet orbit around the galaxy. A cosmic suburb, far from the noise and danger of the galactic downtown. The sun's spectral type is G2V, a classification that tells astronomers about its temperature, size, and luminosity. This seemingly simple code contains a wealth of information about our star's fundamental nature. The letter G indicates the sun's temperature class, cooler than O, B, A, and F stars, but hotter than K and M stars. The number 2 refines this further, placing the sun at the cooler end of the G class, and the Roman numeral 5 indicates it's a main sequence dwarf star, not a giant or supergiant. This classification system, developed in the early 20th century, organizes stars by their spectral characteristics, the specific wavelengths of light they emit and absorb. Each spectral type has distinctive features. O and B stars are blue, hot and short-lived. G stars like the Sun are yellow-white, moderate in temperature and long-lived. M stars are red, cool and extremely long-lived. The Sun's G2V classification tells us it's a fairly typical star, not the hottest, not the coolest, not the biggest, not the smallest, not the brightest, not the dimmest. Just a solid, middle-of-the-road star doing what stars do, fusing hydrogen, shining steadily, providing light and warmth to its planets. And perhaps that ordinariness is part of why life developed here. Extreme stars, the massive blue giants or the tiny red dwarfs, create extreme conditions, but a G2V star, it's stable, predictable, reliable, the kind of star you'd want to orbit if you were hoping to evolve complex life. The Sun formed when a giant molecular cloud collapsed under its own gravity about 4.6 billion years ago. The same collapse that created the Sun also created a spinning disk that became all the planets, including Earth. It's a story of creation from chaos, of order emerging from disorder, of gravity doing what gravity does best, pulling things together. Somewhere in the Milky Way, 4.6 billion years ago, there was a cloud, a vast, cold, dark cloud of gas and dust, hundreds of light years across, drifting through interstellar space. Most of it was hydrogen and helium left over from the Big Bang, but there were also heavier elements, carbon, oxygen, iron, silicon, created in previous generations of stars and scattered into space when these stars died. Something disturbed this cloud. Perhaps a nearby supernova sent a shockwave through it. Perhaps it simply reached a critical density where its own gravity overcame the outward pressure of the gas. Either way, it began to collapse. As it collapsed, it spun faster, flattening into a disk. The center became denser and hotter, until finally the temperature and pressure were high enough for fusion to begin. The Sun ignited, and in the disk around the young Sun, dust particles began to stick together. Tiny grains became pebbles, pebbles became boulders, boulders became planetesimals, planetesimals became planets. Over millions of years, the disk transformed into a solar system, 8 planets, dozens of moons, countless asteroids and comets, all orbiting the newborn star. We are made of this cloud. Every atom in your body was once part of that giant molecular cloud. You are stardust, literally. The calcium in your bones, the iron in your blood, the oxygen in your lungs, it was all floating in that cloud 4.6 billion years ago, waiting to become part of something new. The Sun's surface features granules, convection cells that each last only about 8 to 20 minutes. These bubbling cells of hot plasma are each about the size of Texas, constantly appearing and disappearing. If you could watch the Sun's surface in high resolution, in real time, it would look like a pot of boiling water. Bright cells of hot plasma rise from below, these spreading out as they reach the surface, cooling, and then sinking back down. Each granule is a tiny convection cell, driven by heat from the Sun's interior. Hot plasma rises in the center of the granule, where it appears brighter because it's hotter. As it spreads outward, it cools and darkens, then sinks back down at the edges of the granule, where it appears as dark lanes between the bright centers. And then the process repeats. over and over, years with new granules constantly forming and old ones fading away. The sun's entire photosphere is covered with these granules, millions of them at any given time, creating a mottled, textured appearance. From Earth, we can't see them with the naked eye. The sun just looks like a smooth, featureless disk. But with telescopes equipped with adaptive optics or observing from space, the granulation becomes visible, revealing the sun's surface as a dynamic, churning sea of plasma. It's humbling in a way. These granules, each the size of Texas, each lasting only minutes, are driven by convection currents that extend hundreds of thousands of miles into the sun's interior. They're the visible manifestation of the immense heat engine that powers our star. And they're constantly changing, constantly renewing themselves, a reminder that the sun is never still, never truly the same from one moment to the next. The sun powers Earth's weather, ocean currents, and the water cycle through its radiant energy. Nearly every dynamic process on Earth's surface can trace its energy back to sunlight. The wind blows because the sun heats different parts of the atmosphere unevenly. The ocean currents flow because the sun warms the surface waters near the equator. Rain falls because the sun evaporates water from the oceans and land, lifting it into the atmosphere where it condenses and returns to Earth. Even the energy in fossil fuels, coal, oil, and natural gas, ultimately comes from the sun. Millions of years ago, plants captured sunlight through photosynthesis, converting it into chemical energy. When those plants died and were buried, that stored solar energy was preserved, compressed, and transformed into fossil fuels. When we burn them, we're releasing ancient sunlight, energy that fell on Earth hundreds of millions of years ago. The only major sources of energy on Earth that don't come from the sun are geothermal energy, which comes from Earth's internal heat, and tidal energy, which comes from the gravitational interaction between Earth and the Moon. Almost everything else, wind, solar, hydro, biomass, fossil fuels, is solar energy in one form or another. This makes the sun not just a light in the sky, but the fundamental driver of Earth's climate and weather. Without the sun, there would be no wind, no rain, no ocean currents, no seasons. The atmosphere would freeze and fall to the ground. The oceans would turn to ice. Earth would be a frozen, lifeless ball of rock and ice, drifting silently through the darkness. The sun doesn't just illuminate our world, it animates it, brings it to life, keeps everything moving and changing and evolving. The sun's gravitational influence extends about 2 light years in all directions, defining the solar system's boundary. This sphere of influence, called the Hill sphere, marks where the sun's gravity dominates over other stars. Beyond this distance, the gravitational pull of nearby stars becomes significant, and objects are no longer bound to the sun. This is important when thinking about the Oort cloud, the vast sphere of icy bodies that surrounds the solar system at its outermost edge. The Oort cloud is thought to extend from about 2,000 astronomical units to as far as 100,000 astronomical units from the Sun, roughly halfway to the nearest star. These distant comets are barely held by the Sun's gravity. A passing star could easily disturb them, nudging them into new orbits, sometimes sending them falling toward the inner solar system where they become visible as long-period comets. The Hill sphere defines the maximum size of the solar system in a gravitational sense. Within this boundary, the Sun's gravity is strong enough to hold on to objects despite the gravitational pull of other stars. Outside this boundary, objects are free to wander, to be captured by other stars, to drift through interstellar space as rogue planets or comets. 2 light-years is an enormous distance, about 12 trillion miles, and yet on a galactic scale it's tiny. The nearest star, Proxima Centauri, is about 4.24 light-years away, so there's a gap, a no-man's land between our Hill sphere and theirs, a region where gravity is weak and objects can drift freely. This gap is crossed by the occasional rogue planet or comet, wanderers between the stars, belonging to no one. The Sun produces more energy every second than humanity has used throughout all of history. This perspective highlights both the Sun's immense power and our relatively modest energy consumption. Think about all the energy humanity has ever used, all the fires burned, all the coal mined, all the oil extracted, all the nuclear reactors operated, all the solar panels installed, all the wind turbines spun. Add it all up, across all of human history, from the first campfires to the modern power grid. It's an enormous amount of energy, and the Sun produces that much energy in about 1 second, maybe 2 depending on how you count. The Sun's total power output is so vast that our entire civilization's energy used throughout history is just a rounding error by comparison. This isn't meant to make us feel insignificant exactly. It's more a reminder of the scale of the universe, the sheer abundance of energy flowing through space, most of it unused, unnoticed, just radiating out into the void. And we capture a tiny fraction of the sunlight falling on Earth, less than 0.1%. And from that tiny fraction, we power our civilization, grow our food, warm our homes, run our computers, light our cities. Imagine if we could capture more of it. Imagine if we could harness even 1% of the sunlight falling on Earth. We'd have more energy than we'd know what to do with. The Sun is generous beyond measure, pouring out energy constantly, asking nothing in return. All we have to do is reach out and take it. The Sun's interior is divided into layers. The core, radiative zone and convective zone. Each layer plays a distinct role in transporting energy from the core to the surface. The core, as we've discussed, is where fusion happens, where hydrogen becomes helium, where mass becomes energy, where the Sun's power is generated. It's only about 25% of the Sun's radius, but it contains about half of the Sun's mass. Above the core is the radiative zone. We are extending from about 25% to 70% of the solar radius. In this region, energy moves outward through radiation. Photons are emitted, absorbed, re-emitted, absorbed again, billions and billions of times, slowly working their way outward. The plasma here is dense enough that convection can't occur. The energy has to move by radiation alone. Above the radiative zone is the convective zone, extending from about 70% of the radius to the visible surface. Here, the plasma is cool enough and opaque enough that radiation becomes inefficient. Instead, energy is transported by convection. Hot plasma rises, cools at the surface, and sinks back down. This is where the granules form, where the sun's churning, bubbling motion becomes visible. Each layer has its own physics, its own dynamics, its own timescales. Energy takes thousands of years to cross the radiative zone, but only days to weeks to cross the convective zone. The core rotates differently than the surface. The magnetic field is generated in one layer and emerges in another. The sun is not a uniform ball of gas, but a complex layered structure, each part playing its role in the grand machine that powers our solar system. The sun's chromosphere, a thin layer above the photosphere, appears red during total solar eclipses. This rosy glow comes from hydrogen atoms emitting light at a specific wavelength as they're excited by heat. The chromosphere is only a few thousand miles thick, barely noticeable compared to the sun's radius, but during an eclipse, when the moon blocks the bright photosphere, the chromosphere becomes visible as a thin red ring around the sun's edge. The name chromosphere comes from the Greek word for colour, and it's apt. Unlike the photosphere, which emits a broad spectrum of light that appears white, the chromosphere emits strongly at specific wavelengths, particularly the red H-alpha line of hydrogen. This gives it a distinctive pinkish red colour that's immediately recognisable. The chromosphere is hotter than the photosphere. Temperatures range from about 7,000 to 20,000 degrees Fahrenheit, but cooler than the corona above it. It's a transition region, a boundary between the relatively cool surface and the incredibly hot outer atmosphere. And like everything else on the sun, it's dynamic. The spicules, narrow jets of plasma, shoot upward from the chromosphere into the corona, reaching heights of thousands of miles before falling back down. The chromosphere shimmers and flickers, driven by the churning convection below and the intense magnetic fields threading through it. For most of human history, the chromosphere was visible only during the brief moments of a total solar eclipse. Now, with specialized telescopes that can observe in H-alpha light, we can see the chromosphere any time. But there's still something special about seeing it during an eclipse, that thin red ring surrounding the darkened sun, a glimpse of the hidden layers that lie between the surface we know and the corona we rarely see. The sun experiences supergranulation, convection patterns larger than regular granules that last about 24 hours. These giant cells, about 20,000 miles across, reveal deeper layers of the sun's convective processes. While regular granules are driven by convection near the surface, and supergranules are driven by convection from deeper down, creating larger, longer-lasting patterns. Supergranules are harder to see than regular granules because the brightness contrast is much subtler. They don't show up as bright and dark patches the way granules do. Instead, they're revealed by tracking the horizontal motion of plasma across the sun's surface. Material flows outward from the center of a supergranule and downward at the edges, creating a network of flow patterns that covers the entire sun. Interestingly, magnetic fields tend to concentrate at the boundaries of supergranules, where the downward flows push the field lines together. This is part of how the sun's magnetic field organizes itself at the surface, and it influences where sunspots form and how they evolve. Supergranulation was discovered in the 1950s, much later than regular granulation, because it's so subtle. It took careful observations of Doppler shifts, measuring how fast plasma is moving toward or away from us to reveal these giant convection cells, and there might be even larger convection patterns lurking deeper in the sun, patterns so large and slow-moving that we haven't detected them yet. The sun keeps revealing new layers of complexity the more carefully we look. The sun's gravity keeps all the planets in elliptical orbits, a relationship described by Kepler's laws. These mathematical patterns reveal the elegant simplicity underlying celestial mechanics. In the early 1600s, Johannes Kepler analysed decades of careful observations made by Tycho Brahe and discovered 3 laws that describe planetary motion. The first law states that planets orbit the Sun in ellipses, with the Sun at one focus. The second law states that a line connecting the planet to the Sun sweeps out equal areas in equal times. The third law relates the orbital period to the orbital radius. These laws were empirical. Kepler discovered them by analysing data, not by deriving them from first principles. It wasn't until Isaac Newton came along half a century later that anyone understood why Kepler's laws worked. Newton showed that they were a natural consequence of his law of universal gravitation. Every mass attracts every other mass with a force proportional to their masses and inversely proportional to the square of the distance between them. From this single principle, gravity, all of Kepler's laws emerge. Elliptical orbits, equal areas in equal times, the relationship between period and distance. They're all different ways of describing how objects move under the influence of gravity. And this same principle explains not just planetary orbits, but also satellite orbits, the trajectory of a thrown ball, the tides, the shape of galaxies. Gravity is simple, elegant, and universal. The Sun's gravity holds the solar system together. It keeps Earth at just the right distance, keeps the planets in stable orbits, keeps asteroids and comets from flying off into interstellar space. It's an invisible tether, a force we can't see or feel directly, but one that shapes everything about our existence. Without the Sun's gravity, there would be no solar system, just scattered rocks and gas drifting through the void. The Sun emits energy across the entire electromagnetic spectrum, from radio waves to gamma rays. We only see a narrow slice of this vast range with our eyes, missing most of what the Sun broadcasts. The visible light we see, the colours of the rainbow from red to violet, represents only a tiny fraction of the electromagnetic spectrum. But the Sun produces so much more. In the infrared, beyond the red end of the visible spectrum, the Sun radiates heat. This is the warmth you feel on your skin when you stand in sunlight. In the ultraviolet, beyond the violet end, the Sun produces radiation that can damage DNA and cause sunburn. Earth's atmosphere blocks most UV radiation, which is fortunate for life on the surface. In the X-ray and gamma-ray regions, the Sun produces high-energy radiation, especially during solar flares. And at the other end of the spectrum, in radio waves, the Sun produces low-energy radiation that radio astronomers can detect and study. Each wavelength reveals different aspects of the Sun. Visible light shows us the photosphere. Ultraviolet light reveals the chromosphere and corona. X-rays show us the hottest regions, the active areas where magnetic fields are most intense. Radio waves can penetrate the corona and tell us about conditions in the Sun's atmosphere. by observing the sun across the entire spectrum, we build up a complete picture of what's happening at different heights and temperatures. Our eyes evolve to see visible light because that's what penetrates Earth's atmosphere most efficiently, and what the sun produces most abundantly. But in a sense, we're missing most of the show. The sun is broadcasting in 1,000 different frequencies, and we're tuned to just one narrow band. Then when we use instruments to see the rest, when we look at the sun in ultraviolet or X-rays or radio waves, a whole new sun emerges, stranger and more complex than the simple yellow disk we see in the sky. The sun's convective zone extends from about 70% of the solar radius all the way to the visible surface. In this turbulent region, hot plasma bubbles upward, while cooler plasma sinks, like water boiling in a pot. This is where the sun becomes truly dynamic, where the ordered structure of the radiative zone gives way to churning chaos. Convection happens when radiation becomes inefficient at transporting energy. Deeper in the sun, in the radiative zone, the plasma is hot enough and the density gradient shallow enough that photons can carry energy outward. But in the outer layers, the plasma cools and becomes more opaque. Photons get absorbed more readily and energy piles up. The temperature gradient steepens and eventually it becomes more efficient for the plasma itself to move, carrying energy in bulk. So hot plasma rises, it expands as it rises, cools as it expands, and eventually reaches the surface where it releases its energy as light. Then, cooler and denser, it sinks back down to be reheated. This creates enormous circulation patterns, convection cells at various scales, from the small granules we see on the surface to possibly giant cells that extend through the entire convective zone. This convection is also crucial for generating the sun's magnetic field. The moving plasma carries electric currents, and moving electric currents create magnetic fields. The complex tangled magnetic field we observe at the sun's surface is ultimately driven by the churning convection below. Without convection, the sun would be a much simpler, less active object. It's the turbulence, the chaos, the constant motion that makes the sun interesting. The sun will eventually shed its outer layers and become a white dwarf star about the size of Earth. This dense stellar remnant will slowly cool over trillions of years, eventually becoming a black dwarf. But this end is so far in the future that the universe itself may not be old enough to contain any black dwarfs yet. A white dwarf is what's left when a star like the Sun exhausts its nuclear fuel and sheds its outer layers. The core remains, a dense ball of carbon and oxygen, was compressed by gravity but supported by electron degeneracy pressure. Electron degeneracy pressure is a quantum mechanical effect. Electrons can't be squeezed arbitrarily close together. There's a limit imposed by the Pauli exclusion principle. When matter is compressed enough, this quantum pressure becomes strong enough to support the star against gravity, even without fusion. The result is a white dwarf, an object with about half the Sun's mass compressed into a sphere about the size of Earth. We white dwarfs are incredibly dense. A teaspoon of white dwarf material would weigh several tons. They're also incredibly hot when first formed, up to 100,000 degrees or more. but they have no internal energy source. They're not fusing anything. They're just cooling off, radiating their stored heat into space. And because they're so dense, they cool very slowly. It takes billions of years for a white dwarf to cool to the point where it's no longer glowing visibly. Eventually, after perhaps 10 trillion years or more, a white dwarf will cool enough to stop emitting visible light. At that point, it becomes a black dwarf, a cold, dark cinder drifting through space. But the universe is only 13.8 billion years old. Even the oldest white dwarfs are still warm, still glowing. Black dwarfs are theoretical objects that won't exist for eons. The sun's final state, then, is not oblivion, but a slow fade over timescales almost incomprehensible, a cooling ember that will outlast galaxies. The sun's magnetic field lines can snap and reconnect, releasing enormous amounts of stored energy. This process, called magnetic reconnection, is responsible for solar flares and coronal mass ejections. Imagine stretching a rubber band tighter and tighter. Eventually, if you stretch it too far, it snaps. Magnetic field lines behave similarly. They can be stretched and twisted by the sun's differential rotation and churning convection, storing energy like a wound-up spring. When the field lines become too stressed, too tangled, they can break and reconnect in a lower energy configuration. This releases the stored energy suddenly, violently, in the form of heat, light, and accelerated particles. Temperatures in the reconnection region can reach tens of millions of degrees. Particles are accelerated to near the speed of light, and radiation floods across the electromagnetic spectrum. The physics of magnetic reconnection is complex and still not fully understood. How exactly do field lines break? What triggers the reconnection? How is the energy partitioned between heat, particle acceleration, and radiation? These are active areas of research, studied not just on the Sun but also in Earth's magnetosphere, in laboratory plasmas, and in astrophysical jets around black holes. Magnetic reconnection is one of the fundamental processes in plasma physics, and the Sun is our nearest laboratory for studying it. Every flare, every eruption, every burst of energy from the Sun teaches us something about how magnetic fields behave, how they store energy, and how they release it. The Sun is violent, yes, but it's also instructive. Its fury teaches us physics. The Sun appears to move across the sky due to Earth's rotation, not the Sun's motion. The ancient astronomers struggled with this illusion for centuries before the heliocentric model prevailed. To anyone standing on Earth, the evidence seems overwhelming. The Sun rises in the east, climbs across the sky, and sets in the west. It's moving, obviously, clearly moving. How could it be otherwise? But of course, it's Earth that's moving, spinning on its axis once every 24 hours. The Sun is essentially stationary relative to Earth. Well, not exactly, since Earth is also orbiting the Sun. But that's a slower motion, a yearly cycle rather than a daily one. The daily rising and setting is entirely due to Earth's rotation. This was one of the great conceptual leaps in human history. To accept that the Earth is spinning, that we're moving, that the solid ground beneath our feet is rotating at about 1,000 miles per hour at the equator. It goes against every sensory experience. We don't feel the motion. There's no wind rushing past us, no sense of speed, and yet it's true. The shift from geocentric to heliocentric thinking, from Earth-centered to Sun-centered, was more than just an astronomical correction. It was a philosophical revolution. It displaced humanity from the center of the cosmos. It suggested that our perspective might be misleading, that what seems obviously true might not be, and it opened the door to a new way of thinking about the universe, one based on observation, mathematics, and the willingness to question appearances. The sun doesn't move across our sky. We move beneath it, and in accepting that, we took a step toward understanding our true place in the universe. The sun's radiation pressure keeps comets' tails pointing away from it, even when comets are moving away from the sun. This creates the beautiful paradox of comet tails that can point forward in the comet's orbit. When most people think about a comet, they imagine it streaking across the sky with its tail trailing behind it, like the contrail behind a jet. But that's not how comet tails work. A comet has two tails, actually. The dust tail is pushed away from the sun by light pressure, and it curves gently, following the comet's orbital path. The ion tail, made of charged gas, is pushed away by the solar wind, and it points directly away from the sun, regardless of which direction the comet is moving. So when a comet is approaching the sun, its tails point backward, away from the sun and away from the direction of motion. But when the comet is moving away from the sun, its tails point forward, still away from the sun but now in the direction of motion. This was puzzling to early astronomers who didn't understand light pressure or solar wind. Why would a comet's tail point forward? It seemed to violate the laws of motion. But once we understood that the tail isn't caused by the comet's motion through space, but by the sun's influence, it made sense. The tail doesn't trail behind the comet. It's blown away from the sun, like smoke from a candle blown by a fan, regardless of which way the candle is moving. It's a reminder that space isn't like Earth's surface. There's no air resistance, no friction, no intuitive sense of forward and backward. Objects move according to gravity and radiation pressure, not according to the rules we learn from everyday experience. And sometimes that leads to behaviors that seem paradoxical or impossible, until we adjust our thinking and understand the real forces at play. The sun produces about 4 times 10 to the 26th power watts of power, a number almost impossible to comprehend. This is roughly equivalent to the energy of 100 billion nuclear bombs exploding every single second. Let's try to put that in perspective. A typical nuclear bomb releases about 100 trillion joules of energy. That's an enormous amount, enough to level a city. Now multiply that by 100 billion. That's how much energy the sun releases every second. Not every year, not every day, every single second. And it's been doing this for 4.6 billion years. Every second of every minute of every hour of every day for billions of years, the sun has been outputting this staggering amount of energy, and it will continue for billions more. The total amount of energy the sun has released over its lifetime is so vast that there's no useful analogy for it. It's beyond human comprehension, beyond the scale of anything we experience, and yet from our perspective, 93 million miles away, receiving only a tiny fraction of this output, The sun is just pleasant. It's the warmth on a summer day. It's the light streaming through a window. It's gentle, nurturing, life-giving. The sun is simultaneously the most powerful thing in our immediate cosmic neighborhood and the most benign. It's a controlled thermonuclear explosion, held in check by gravity, radiating energy in all directions. And we exist in the narrow band where that energy is neither too much nor too little, but just right. The sun's atmosphere is threaded with magnetic field lines that guide the flow of charged particles. These invisible lines create the beautiful, complex structures we see in solar prominences and coronal loops. If you could see magnetic field lines, the sun would look like a tangled ball of yarn, with lines looping and arcing and spiraling in intricate patterns. Your just charged particles, electrons and protons, can't cross magnetic field lines easily. They're constrained to move along them, spiraling around them like beads on a wire. So when magnetic field lines arch from one point on the sun's surface to another, plasma flows along those arches, creating the glowing loops we see in ultraviolet and X-ray images. When field lines extend outward into space, plasma flows along them into the solar wind. These magnetic structures are constantly evolving. The field lines emerge from below the surface, rise into the atmosphere, twist and tangle, reconnect, collapse, and re-emerge. It's a continuous dance, driven by the churning convection below and shaped by the complex physics of plasma and magnetism. And these structures have real effects. They heat the corona to millions of degrees. They accelerate the solar wind. They store energy that's released in flares. They create the dynamic, ever-changing appearance of the sun's atmosphere. And the sun isn't just a ball of hot gas. It's a magnetic organism, shaped and guided by invisible fields, constantly reorganizing itself, constantly creating new structures and destroying old ones. The sun's chemical composition is about 73% hydrogen, 25% helium, and 2% heavier elements. This mix reflects the primordial composition of the universe, only slightly enriched by previous generations of stars. When the universe began, about 13.8 billion years ago, the Big Bang created mostly hydrogen and helium, with trace amounts of lithium. That's it. No carbon, no oxygen, no iron, no silicon. All the heavier elements were made later, in stars. The first generation of stars, population 3 stars as they are called, formed from this primordial gas. They were made of pure hydrogen and helium. When they died, they scattered heavier elements into space, enriching the interstellar medium. The next generation of stars formed from this enriched gas, and they contained a small amount of heavy elements. They lived, died, and enriched the gas further, and so on, generation after generation, each cycle adding more heavy elements to the cosmic mix. The sun is a third-generation star, or maybe fourth, it's hard to say exactly, but it formed from gas that had already been enriched by previous stars. That's why it contains 2% heavy elements: carbon, oxygen, iron, silicon, and all the others. Those elements are the ashes of long-dead stars, which mixed into the cloud that collapsed to form the sun and the solar system. And those heavy elements are crucial for us. You can't make planets like Earth out of pure hydrogen and helium. You need rock, metal, elements heavy enough to condense into solid matter. and you certainly can't make life without carbon, oxygen, nitrogen, phosphorus, and other heavy elements. We exist because previous stars lived and died, because they created the elements we're made of and scattered them into space, and we are quite literally made of stardust. The Sun undergoes periods of reduced activity called grand minimums, which can last for decades. The Maunder minimum from 1645 to 1715 coincided with the Little Ice Age on Earth, though the connection is still debated. During the Maunder minimum, sunspots almost completely disappeared. For 70 years, the Sun's face was nearly blank. Observers at the time noted the absence, but didn't understand what it meant. Interestingly, this period coincided with unusually cold temperatures in Europe and North America. The Thames River in London froze over regularly. Glaciers advanced in the Alps. Crop failures were common. This period is sometimes called the Little Ice Age, and some scientists have suggested a connection to the Sun's reduced activity. The mechanism is unclear. The Sun's total energy output doesn't vary much during grand minimums, certainly not enough to directly cause significant climate change. But there might be indirect effects. Changes in the Sun's ultraviolet output could affect Earth's upper atmosphere, which could influence weather patterns. Changes in the solar wind and cosmic ray flux could affect cloud formation. The details are still being researched, still being debated. What's clear is that the Sun's activity isn't perfectly regular. The 11-year cycle is an average, and sometimes the Sun deviates from it significantly. Grand minimums seem to occur every few centuries, and there are hints of grand maximums as well, periods of unusually high activity. The Sun has moods, in a sense. Sometimes it's active and energetic, sometimes it's quiet and subdued, and these moods might, just might, have subtle effects on Earth's climate. Not enough to override human-caused climate change in the modern era, but enough to matter in pre-industrial times when natural variations dominated. The Sun's radiative zone is so dense that energy moves through it only by radiation, or not convection. Photons can travel only a tiny distance before being absorbed and re-emitted, making progress through this zone agonizingly slow. In the radiative zone, which extends from about 25% to 70% of the Sun's radius, the plasma is incredibly dense and hot. Dense enough that photons can barely move. A photon is emitted by a hot atom, travels perhaps a fraction of a millimeter, and is absorbed by another atom. That atom re-emits a photon, or usually at a slightly different wavelength and in a random direction. That photon travels another tiny distance and is absorbed again. Over and over, billions upon billions of times, the energy slowly diffuses outward through this dense soup of matter. This is why photons take tens of thousands of years to cross the radiative zone, despite traveling at the speed of light. They're not moving in a straight line. They're performing a random walk, taking countless tiny steps in random directions. We're only gradually making net progress outward. It's like trying to walk across a crowded room where you can only take one step before bumping into someone and being redirected in a random direction. Eventually you'll make it across, but it will take much longer than if you could walk straight. The radiative zone is stable, orderly, almost serene compared to the churning convective zone above it. There's no bulk motion of plasma, no turbulence, no visible structure, a just endless absorption and emission. Photons diffusing outward through the dense interior, carrying the sun's energy from the core toward the surface. It's a quiet journey, hidden from view, but essential to how the sun works. The sun's gravity creates a gravitational lens effect, theoretically allowing it to magnify distant objects. A telescope positioned at the right distance beyond the sun could potentially image exoplanets in extraordinary detail. This is one of the more exotic applications of Einstein's general relativity, the idea that massive objects bend light, creating a kind of gravitational lens. The sun's gravity warps space-time around it, and light passing near the sun follows this curved path. If you position a telescope at the right spot, about 550 astronomical units from the sun, roughly 14 times farther than Pluto, light from a distant object can be bent around the sun and focused at that point. The sun acts like a giant lens, magnifying the distant object. The magnification would be enormous, potentially enough to image the surface features of exoplanets dozens or even hundreds of light years away. We could see continents, oceans, cloud patterns, maybe even signs of life. It's an incredibly exciting possibility, and several mission concepts have been proposed to take advantage of it. Of course, there are challenges. Getting a spacecraft to 550 astronomical units would take decades, even with advanced propulsion. Positioning it precisely enough to capture the focused light would be difficult, and the sun itself is a very bright object, so you'd need to block its light carefully to see the faint magnified image. But the potential payoff is so great that it's worth exploring. The sun, already so generous with its energy, might also give us a tool to see distant worlds in unprecedented detail. The sun produces tiny amounts of antimatter in its core through nuclear reactions. These antiparticles immediately annihilate with regular matter, contributing to the sun's energy output. Antimatter sounds like science fiction, but it's real, and it's being created in the sun right now. During certain fusion reactions, positrons, the antimatter equivalent of electrons, are produced as byproducts. These positrons don't last long. The sun's core is incredibly dense, full of regular matter. Within a fraction of a second, each positron encounters an electron, and they annihilate each other, converting their mass entirely into energy in the form of gamma rays. This annihilation energy contributes to the sun's total output, though it's a small fraction of the energy released by fusion itself. The fact that antimatter exists in the sun is a reminder that exotic physics isn't confined to laboratories or distant cosmic events. It's happening all around us, all the time, in the heart of our own star. Matter and antimatter, creation and annihilation, be all part of the normal operation of the fusion reactions that power the sun. Antimatter is often portrayed as rare, dangerous, impossibly exotic, and it's true that it's difficult to create and store in large quantities on Earth. But in the sun's core, it's just another part of the process, another step in the chain of reactions that converts hydrogen into helium and mass into energy. The universe is stranger than we often imagine, and some of that strangeness is happening right overhead. Hidden in the sun's glowing heart, The sun's oscillations caused by sound waves reverberating through its interior help scientists study its structure. This field, called helioseismology, works like a cosmic ultrasound, revealing the sun's hidden layers. Just as geologists use seismic waves from earthquakes to study Earth's interior, solar physicists use sound waves to study the sun's interior. These sound waves are created by the churning convection at the sun's surface. The turbulent plasma creates pressure waves, essentially sound waves, that propagate into the interior. When these waves encounter regions of different density or temperature, they're reflected or refracted, changing their path. Eventually they return to the surface, where they create tiny oscillations, the surface rising and falling by a few meters, with periods of a few minutes. By measuring these oscillations across the sun's surface, these scientists can infer the properties of the interior, how dense it is at different depths, how hot, how the rotation rate varies with depth. It's like ringing a bell and listening to the overtones to determine what the bell is made of. Different oscillation patterns correspond to different acoustic modes, each probing different parts of the sun's interior. Helioseismology has taught us things we could never learn from surface observations alone. We've measured the rotation rate of the sun's core. We've determined the location of the boundary between the radiative and convective zones. We've detected flows and currents deep inside the sun. The sun is opaque. We can't see inside it directly, but we can listen to it, and by listening, we can understand what's hidden beneath the surface. The sun influences Earth's climate on long timescales, through variations in its energy output and orbital mechanics. These Milankovitch cycles help explain ice ages and warm periods throughout Earth's history. Earth's orbit isn't perfectly stable. It changes over tens of thousands of years. The orbit becomes more or less elliptical. The tilt of Earth's axis wobbles. The direction the axis points precesses, like a spinning top slowly tracing a circle. These changes, named after Serbian scientist Milutin Milankovitch, who studied them extensively, affect how much sunlight different parts of Earth receive at different times of year. When the northern hemisphere receives less summer sunlight, snow and ice can accumulate year-round, triggering an ice age. When it receives more, ice melts and the climate warms. The sun's brightness also varies slightly over long periods. Not the 11-year cycle, but slower variations over thousands or even millions of years. These changes are small, but combined with orbital variations, they can tip Earth's climate from one state to another. It's a reminder that climate is influenced by many factors, operating on many timescales. Human-caused climate change is currently the dominant factor, overwhelming natural variations. But on longer timescales, tens of thousands to millions of years, orbital mechanics and solar variations matter. The sun and Earth dance together, their relationship changing slowly over time, and that dance has consequences for ice sheets and ocean levels and the conditions for life. The sun's magnetic field reversal process is not instantaneous, but takes about a year to complete. During this transition period, the sun can briefly have multiple magnetic poles simultaneously. This is one of the stranger aspects of the solar cycle. You might imagine the magnetic field flipping suddenly, like throwing a switch. But it's not that simple. The sun's magnetic field is complex, regenerated by different layers rotating at different speeds, with different parts of the field evolving on different timescales. So when the field reverses, different regions reverse at different times. For a while, the sun might have 4 poles, 2 north and 2 south, or a more chaotic configuration with no clear poles at all. Eventually, the field settles into a new bipolar structure with reversed polarity, and the cycle begins again. This transition period is usually marked by high solar activity. Sunspots are numerous, flares are frequent, the corona is complex and structured. The sun is reorganizing its magnetic personality, and the process is messy, turbulent, energetic. Then, once the reversal is complete, activity begins to decline, and the sun heads toward the next solar minimum. It's a reminder that magnetic fields aren't simple, static things. They're dynamic, evolving, shaped by the motion of electrically conducting fluids. And on the sun, where the entire object is fluid, where different parts rotate at different speeds, the magnetic field takes on a life of its own, constantly changing, constantly reorganizing, never truly stable. The sun will lose about half its mass when it becomes a red giant, loosening its gravitational hold on the planets. Earth's orbit will expand as the sun's mass decreases, possibly saving us from being engulfed. This is one of the more hopeful aspects of the sun's eventual death, at least from Earth's perspective. When the sun expands into a red giant, it will grow enormous, possibly reaching the orbit of Mars. The inner planets, Mercury, Venus, possibly Earth, seem doomed to be swallowed. But as the sun swells, it will also lose mass. The outer layers will be loosely bound, and the solar wind will become a gale, blowing material away into space. Over the course of a few 100 million years, the sun might lose 30% to 50% of its mass. And as the sun's mass decreases, its gravitational pull weakens. The planet's orbits, no longer held as tightly, will spiral outward. Whether this is enough to save Earth is uncertain. Different models give different answers, depending on the details of how the sun loses mass and how tidal forces affect Earth's orbit. Some models suggest Earth will escape, settling into a new, wider orbit around the bloated red giant. Others suggest it will be engulfed, is vaporized in the sun's extended atmosphere. Either way, Earth won't be habitable. Even if the planet physically survives, it will be baked to temperatures of hundreds or thousands of degrees. The oceans will boil away, the atmosphere will be stripped off, any life that still exists will be annihilated. Earth might survive as a charred rock, but it won't be Earth as we know it. The end of the sun's life is the end of Earth's life, regardless of the precise details. The sun produces subtle variations in brightness due to dark sunspots and bright faculae on its surface. These variations are small enough that Earth's climate system can handle them, but large enough to measure precisely. When the sun has many sunspots, you might expect it to be dimmer. After all, sunspots are cooler, darker regions. But actually the sun is slightly brighter during solar maximum. Now this is because of faculae, bright regions associated with magnetic activity that more than compensate for the dark sunspots. Faculae are hotter than the surrounding photosphere, and appear as bright patches, especially near the limb of the Sun where the contrast is most visible. During solar maximum there are more faculae as well as more sunspots, and the faculae win, making the Sun slightly brighter overall. The total variation is about 0.1%, tiny but measurable with sensitive instruments. Over the 11-year solar cycle, the Sun's energy output varies by this small amount, and Earth receives correspondingly more or less energy. This isn't enough to cause dramatic climate swings, but it does have subtle effects that can be detected in historical climate records. These variations remind us that the Sun isn't a perfect, unchanging light bulb. It's a dynamic, active object with surface features that come and go, affecting its brightness in measurable ways. But it's also remarkably stable compared to many other stars. Some stars vary by 10%, 20%, even 50% in brightness. The Sun's 0.1% variation is modest, gentle, the kind of stability that allows complex life to develop and persist. The Sun's energy doesn't distribute evenly across Earth, creating the climate zones and weather patterns we experience. The equator receives more direct sunlight than the poles, driving the global circulation of air and water. This uneven heating is the fundamental driver of Earth's weather and climate. At the equator, sunlight strikes nearly straight down, delivering maximum energy per unit area. At the poles, sunlight strikes at a steep angle, spreading the same amount of energy over a much larger area. The result is that the equator is hot and the poles are cold. This temperature difference drives atmospheric circulation. Hot air rises at the equator, flows toward the poles at high altitude, sinks at mid-latitudes, and returns toward the equator at the surface. This creates the trade winds, the westerlies, the polar easterlies, the major wind patterns that shape weather across the globe. The same temperature difference drives ocean currents. Warm water flows from the equator toward the poles at the surface. Cold water flows back toward the equator at depth. These currents, like the Gulf Stream in the Atlantic, transport enormous amounts of heat around the planet, moderating climates and influencing weather patterns. All of this, the wind, the rain, the ocean currents, the seasons, is driven by the simple fact that the Sun shines more directly on some parts of Earth than others. The Sun's energy arrives evenly, but Earth's curved surface means it's absorbed unevenly. And from that unevenness, all the complexity of weather and climate emerges. Hurricanes, monsoons, droughts, blizzards, all traces back to the Sun shining on a spinning, tilted sphere. The Sun's gravitational influence creates Lagrange points, stable locations where spacecraft can park in space. Several solar observatories sit at the Sun-Earth L1 point, maintaining a constant view of our star. Lagrange points are special locations where the gravitational pull of two large bodies, in this case the Sun and Earth, combine with the centrifugal force of the orbital motion to create a stable equilibrium. There are 5 Lagrange points in the Sun-Earth system. One L1 is between the Sun and Earth, about 1 million miles from Earth. A spacecraft placed there orbits the Sun at the same rate as Earth, maintaining a fixed position relative to Earth while having an unobstructed view of the Sun. This makes it ideal for solar observatories like SOHO, which has been stationed there since 1996. L2 is on the opposite side of Earth from the Sun, also about 1 million miles away. It's a good location for space telescopes that need to stay cool and avoid sunlight. Like the James Webb Space Telescope, L3 is on the opposite side of the Sun from Earth. L4 and L5 are 60 degrees ahead and behind Earth in its orbit, locations where the gravitational balance is particularly stable. These points aren't perfectly stable. Spacecraft need occasional course corrections to stay there, but they're close enough to stable that they're useful for long-term missions. They're like cosmic parking spots, places where gravity balances out, where you can station a telescope or observatory and it will more or less stay put, orbiting with the Earth, always in the right position to observe the Sun or deep space or whatever you're interested in. The Sun experiences dramatic eruptions called coronal mass ejections that can disrupt Earth's magnetic field. These massive clouds of plasma can travel from the Sun to Earth in as little as 15 to 18 hours. A coronal mass ejection, or CME, is like a solar hurricane, a billion-ton cloud of magnetized plasma ejected from the Sun's corona, racing through space at speeds that can exceed 1 million miles per hour. When a CME is Earth-directed, it carries with it a portion of the Sun's magnetic field twisted and compressed into a massive structure. When this magnetic cloud reaches Earth, it collides with our planet's magnetosphere, the protective magnetic bubble that surrounds us. The impact compresses the magnetosphere, sometimes pushing it back so dramatically that satellites in high orbits find themselves temporarily outside Earth's magnetic protection. This compression and the resulting magnetic reconnection inject enormous amounts of energy into Earth's magnetosphere. Charged particles spiral down magnetic field lines toward the poles, creating spectacular auroras that can be visible at much lower latitudes than usual. During powerful geomagnetic storms, auroras have been seen as far south as the Caribbean or the Mediterranean, but there are also dangers. The changing magnetic fields can induce electric currents in power lines, potentially damaging transformers and causing blackouts. In 1989, a strong geomagnetic storm caused a 9-hour blackout across Quebec. Satellites can be damaged or disrupted. GPS signals can become unreliable. Radio communications can be interrupted. The Sun, even from 93 million miles away, can reach out and affect our technology, our infrastructure, our daily lives. The Sun's rotation axis is tilted about 7.25 degrees relative to the plane of Earth's orbit. This slight tilt means we see different solar latitudes throughout the year, affecting our view of sunspots. As Earth orbits the Sun, our perspective changes slightly. In September, we see more of the Sun's northern hemisphere. In March, we see more of the southern hemisphere. These changes which sunspots are visible, and how prominently we can see features at different latitudes. The tilt also means that the Sun's equator doesn't align with the ecliptic, the plane in which Earth and the other planets orbit. This misalignment might seem like a trivial detail, but it tells us something about the Sun's history. When the solar system formed from a rotating disk of gas and dust, you'd expect everything to be aligned. The Sun's rotation, the planet's orbits, all in the same plane. The fact that they're not perfectly aligned suggests that something disturbed the system early on. Perhaps gravitational interactions with Jupiter, the most massive planet, tugged the Sun's rotation axis slightly out of alignment. Perhaps turbulence in the protoplanetary disk affected how angular momentum was distributed. The exact cause is still debated, but the misalignment itself is evidence that the early solar system was a dynamic, chaotic place, not the orderly, aligned system we might naively expect. These small details, a few degrees of tilt, a slight misalignment, carry clues about the solar system's violent birth, about the forces that shaped it, about the complex dance of gravity and angular momentum that turned a cloud of gas into a star and its family of planets. The Sun fuses about 620 million tons of hydrogen every second, but only loses 4 million tons as energy. The difference, 616 million tons, becomes helium ash that accumulates in the core. This distinction is important. The fusion process doesn't make all the hydrogen disappear. Most of it gets converted into helium, which remains in the core, gradually building up over billions of years. Only about 0.7% of the hydrogen's mass is actually converted into energy through Einstein's E equals mc squared. That 0.7%, about 4 million tons per second, is released as photons and neutrinos, carrying energy outward from the core. The rest becomes helium, denser and heavier than hydrogen, sinking toward the center of the core. Over billions of years, this helium ash accumulates. The core becomes increasingly helium-rich, while the surrounding layers remain mostly hydrogen. Eventually, when the core runs out of hydrogen to fuse, it will be nearly pure helium, the accumulated product of 10 billion years of fusion. And then, if the core gets hot enough, helium fusion will begin, converting 3 helium nuclei into 1 carbon nucleus, creating a new layer of ash. The Sun is like a cosmic furnace with an ash pile that never gets cleaned out. The ashes just accumulate layer upon layer, each representing a different phase of the Sun's life. Hydrogen ash becomes helium, helium ash becomes carbon and oxygen, and for stars more massive than the Sun, the process continues. Carbon ash, neon ash, silicon ash, iron ash, until finally, the furnace can burn no more. The Sun's surface has a turbulent, ever-changing appearance when viewed in high resolution. Here, what appears as a smooth, featureless disk to the naked eye is actually a roiling, boiling surface. With a good telescope and the right atmospheric conditions, or better yet observing from space, the Sun's photosphere reveals itself as a complex textured landscape. Granules bubble and churn, each one the size of Texas, appearing and disappearing every few minutes. Sunspots drift slowly across the surface, evolving in shape and size, sometimes merging, sometimes splitting apart. Bright faculae shimmer near active regions. The limb of the Sun, the edge as seen from Earth, appears darker than the center due to limb darkening, a perspective effect caused by seeing deeper, hotter layers when looking at the center than when looking at the edge. In time-lapse videos taken from solar observatories, the Sun's surface looks alive. It ripples, flows, pulses with energy. Plasma fountains erupt from sunspots, arcing thousands of miles into the chromosphere before falling back. Waves propagate across the surface, visible as subtle oscillations in brightness. The Sun is never still. never truly at rest. And this is just the photosphere, the surface we can see in visible light. In ultraviolet, the chromosphere reveals even more complexity. Spicules shooting upward like blades of grass, prominences arcing between sunspots, the delicate structure of the corona threading through space. In X-rays, the hottest regions glow brightly, revealing active areas where magnetic energy is being released. Each wavelength reveals a different layer, a different aspect of the sun's complex dynamic nature. The sun produces approximately 2% of its energy through secondary fusion reactions involving helium-3. These reactions produce different neutrinos than the primary proton-proton chain, giving us clues about solar physics. The main fusion process in the Sun, called the proton-proton chain, involves several steps. 2 protons fuse to form deuterium, releasing a positron and a neutrino. The deuterium fuses with another proton to form helium-3, and then, most commonly, 2 helium-3 nuclei fuse to form helium-4, releasing 2 protons as the process. But there are alternative pathways. Sometimes, helium-3 fuses with existing helium-4 to form beryllium-7, which can then capture a proton to form boron-8, which decays to beryllium-8, which splits into 2 helium-4 nuclei. This pathway produces higher energy neutrinos that we can detect on Earth. By measuring the flux of neutrinos at different energies, scientists can determine which fusion reactions are occurring in the Sun's core and at what rates. This is important because it tests our understanding of solar physics. For many years, the observed neutrino flux was lower than predicted, a puzzle called the solar neutrino problem. The solution turned out to involve neutrino oscillations, neutrinos changing from one type to another as they travel from the Sun to Earth. The Sun's fusion reactions produce electron neutrinos, but by the time they reach Earth, some have oscillated into muon or tau neutrinos, which the early detectors couldn't see. Once we understood this, and built detectors that could see all types of neutrinos, the measurements matched predictions. The Sun taught us something fundamental about particle physics, about neutrinos, about the subtle ways the universe works. The Sun's influence on Earth extends beyond light and heat to include its magnetic field's interaction with our magnetosphere. This interaction creates the beautiful auroras and protects us from harmful cosmic radiation. Earth's magnetic field acts as a shield, deflecting most of the solar wind around us. But the interaction isn't passive, it's dynamic, energetic, constantly changing. When solar wind particles encounter Earth's magnetic field, they compress it on the day side and stretch it into a long tail on the night side. Magnetic field lines on the day side get pushed together. On the night side, they get pulled apart and eventually snap back together in a process called magnetic reconnection, similar to what happens in solar flares. This reconnection releases energy, accelerating particles down magnetic field lines toward Earth's poles. When these particles collide with atoms in the upper atmosphere, oxygen and nitrogen mostly, they excite those atoms, causing them to emit light. Oxygen produces green and red auroras. Nitrogen produces blue and purple. The result is the shimmering, dancing curtains of light we call the aurora borealis and aurora australis. But the magnetosphere does more than create pretty lights. It protects us from cosmic radiation, high-energy particles from the sun, and from deep space that could damage DNA and harm living tissue. Without the magnetosphere, Earth's surface would be bathed in much higher levels of radiation, making life more difficult, perhaps impossible. The sun gives us light and warmth, yes, but it also gives us danger. And Earth's magnetic field, powered by the churning of molten iron in our planet's core, shields us from that danger. It's a delicate balance, a cosmic symbiosis between star and planet. The sun's diameter is about 109 times larger than Earth's, but its density is only about 1/4 that of Earth. Despite its immense size, the sun is primarily composed of the lightest elements in the universe. This is one of those facts that seems contradictory at first. The sun is massive, 333,000 times Earth's mass. How can it be less dense? The answer is that the sun is made mostly of hydrogen and helium, the two lightest elements. Earth, by contrast, is made of rock and metal, silicon, iron, nickel, oxygen, much heavier elements. Even though the sun's core is incredibly dense due to the immense pressure, the average density across the entire sun is only about 1.4 grams per cubic centimetre. For comparison, Earth's average density is about 5.5 grams per cubic centimetre. This means that if you could somehow place the sun and Earth on a giant cosmic scale and measure their density, Earth would be the denser object, whereas despite being vastly smaller, the sun is voluminous but light, at least on average. Its outer layers are so tenuous they're nearly a vacuum by our standards. This low average density is typical for stars. They're made of the lightest stuff in the universe, puffed up by heat and rotation into enormous spheres. Planets, especially rocky ones, are made of the heavy elements that sink to the bottom of the cosmic mixing bowl, the iron, silicon, and other elements that can form solid structures. The sun and Earth are made of the same basic ingredients but sorted by weight. The light stuff became the sun, the heavy stuff became the planets. The sun will spend about 10 billion years on the main sequence before evolving into a red giant. We're currently about halfway through the sun's stable, life-supporting phase. The sun is middle-aged in cosmic terms. It's been fusing hydrogen for 4.6 billion years, and it has enough fuel left to continue for another 5 billion or so. This is worth appreciating. The sun's stability over billions of years is what made complex life possible on Earth. Evolution is a slow process, requiring stable conditions over immense timescales. If the sun were a variable star, brightening and dimming dramatically over thousands or millions of years, Earth's climate would swing wildly. Ice ages and hothouse periods would come and go with no pattern. Life might adapt to brief windows of favourable conditions, but developing complex ecosystems, let alone intelligent life, would be nearly impossible. But the sun is steady. It brightens slowly over billions of years, but the change is gradual enough that planetary systems can adjust. Earth's climate has changed over geological time, yes, but mostly due to factors other than the sun: volcanic activity, continental drift, changes in atmospheric composition, asteroid impacts. The sun itself has been a constant, reliable presence. We exist in the middle of the sun's life, in the sweet spot where it's stable and predictable. If we'd evolved earlier during the sun's tumultuous youth when it was more variable and active, life might have struggled. If we evolved later, during the sun's decline into a red giant, we'd have no future to look forward to. But here, now, in the sun's middle age, conditions are as good as they're ever going to be. We should probably make the most of it. The sun's acoustic waves take about an hour to travel from the core to the surface. These sound waves bounce around inside the sun, creating the oscillations that helioseismologists study. Sound travels at different speeds depending on the temperature and composition of the material it's passing through. In the sun's hot, dense core, sound waves move faster than at the cooler, less dense surface. These waves are created by turbulence in the convective zone. The constant churning and bubbling creates pressure fluctuations that propagate as sound. The waves dive into the interior, they refract through layers of different density and return to the surface, where they create the oscillations we can measure. Different waves take different paths, probing different parts of the sun's interior. By analyzing millions of these oscillations, measuring their frequencies and how they change over time, scientists can map the sun's interior structure. They can determine where the convective zone ends and the radiative zone begins. They can measure rotation rates at different depths and latitudes. They can detect flows and currents deep inside the sun. It's like medical imaging using sound waves to see inside a patient, except the patient is a star. The sun rings like a bell, constantly, with millions of different overtones all playing at once. We can't hear it. Sound doesn't travel through the vacuum of space, and even if it did, the frequencies are too low for human ears. But we can measure it, and by measuring it, we can see inside the sun, revealing secrets that would otherwise remain hidden beneath the glowing surface. The sun's activity affects the amount of carbon-14 produced in Earth's atmosphere. This allows scientists to reconstruct solar activity levels from tree rings and ice cores stretching back thousands of years. Carbon-14 is a radioactive isotope created when cosmic rays strike nitrogen atoms in the upper atmosphere. These cosmic rays come from deep space, but their flux is modulated by the sun's magnetic field and solar wind. During periods of high solar activity, the sun's magnetic field is stronger and the solar wind more intense, deflecting more cosmic rays away from Earth. This reduces carbon-14 production. During periods of low solar activity, more cosmic rays reach Earth, and carbon-14 production increases. The carbon-14 is incorporated into carbon dioxide, absorbed by plants through photosynthesis and preserved in tree rings. By measuring the carbon-14 content in tree rings of known ages, scientists can reconstruct solar activity levels going back thousands of years. Ice cores provide a similar record. Cosmic ray interactions create other isotopes that get trapped in snow and preserved as it compresses into ice. These records show that the 11-year solar cycle has been operating for at least several thousand years, and they've revealed grand minimums like the Maunder minimum that wouldn't be known from direct observations alone. It's a beautiful example of how everything is connected. The sun's magnetic field affects cosmic rays. Cosmic rays affect carbon-14. Carbon-14 affects tree rings. And by reading tree rings, we can learn about the sun's history. The universe leaves traces, records of its behavior encoded in ice and wood, waiting to be read by anyone curious enough to look. The sun produces a steady stream of solar wind that thins out as it travels through the solar system. By the time solar wind reaches Earth, it's been diluted to just a few particles per cubic centimetre. In the sun's corona, near the surface, the solar wind is relatively dense, millions of particles per cubic centimetre. But as it expands outward, spreading into the vast volume of space, it thins dramatically. This is a consequence of geometry. As the solar wind flows outward, yes, it spreads over an ever-increasing sphere. This surface area of a sphere grows with the square of the radius, so the density drops with the square of the distance from the sun. By the time the solar wind reaches Earth, 93 million miles away, it's been diluted to about 5 particles per cubic centimetre. For comparison, Earth's atmosphere at sea level contains about 10 to the power of 19 molecules per cubic centimetre. Even the best vacuum we can create in a laboratory contains billions of particles per cubic centimetre. The solar wind at Earth's distance is emptier than the emptiest vacuum chamber humans have ever built. And yet, even this tenuous flow has real effects. It carries the sun's magnetic field throughout the solar system. It creates pressure that shapes planetary magnetospheres. It accelerates particles to high energies during magnetic storms, where the solar wind continues thinning as it travels outward. By the time it reaches the heliopause, the boundary where it meets the interstellar medium, it's been diluted to a tiny fraction of its original density. But it never stops completely. The sun's breath flows outward continuously, filling the solar system with its presence, however tenuous. Even in the most remote corners of our cosmic neighbourhood, the sun makes itself known. The sun's powerful gravity creates extreme time dilation effects, though less dramatic than near a black hole. Time actually passes slightly slower at the sun's surface than it does here on Earth. This is a consequence of Einstein's general relativity. Gravity warps space-time, and one of the effects of this warping is that time runs slower in stronger gravitational fields. The effect is small, about 67 parts per billion. This means that for every billion seconds that pass on Earth, about 67 fewer seconds pass at the sun's surface. Over a year, this amounts to about 2 seconds. It's not the kind of time dilation you'd notice in everyday life, but it's measurable with precise atomic clocks. Near a black hole, where gravity is far stronger, the effect becomes dramatic. Time can slow to a crawl near the event horizon. But the sun, while massive, isn't dense enough to create such extreme effects. Its gravity is strong enough to hold the solar system together, and strong enough to compress its core to fusion temperatures, but not strong enough to dramatically warp time. Still, the effect is there. A subtle reminder that space and time aren't absolute, that they're flexible, malleable, influenced by mass and energy. The sun doesn't just pull on objects with its gravity, it pulls on time itself, ever so slightly, stretching and compressing the fabric of space-time. Einstein's universe is stranger than Newton's, and the sun, familiar as it is, lives in Einstein's universe, where clocks run at different rates depending on where you are. The sun's nuclear fusion reactions create electron neutrinos that we can detect here on Earth. These observations confirmed our understanding of how the sun produces energy and helped reveal neutrino oscillation. For decades, physicists believed they understood the sun's fusion process. The proton-proton chain should produce a specific flux of electron neutrinos, and we should be able to detect them with sensitive underground detectors. But when the detectors started operating in the 1960s, they found a problem. They were only detecting about 1/3 of the expected neutrinos. This was deeply puzzling. Either our understanding of the sun was wrong, or our understanding of neutrinos was wrong. For years, the solar neutrino problem remained one of the great mysteries in physics. The solution came from an unexpected direction. Neutrinos, it turns out, we can change their flavor, oscillating between electron neutrinos, muon neutrinos, and tau neutrinos as they travel. The early detectors could only see electron neutrinos, so they missed the 2/3 that had oscillated into other flavors during their 8-minute journey from the sun to Earth. Once new detectors were built that could see all 3 flavors, the total neutrino flux matched predictions perfectly. The sun was fine. Our understanding of fusion was correct. But we learned something new about neutrinos. They have mass, they oscillate. They're more complex than we thought. The sun, by simply shining, taught us fundamental physics. Its neutrinos, ghostly and barely detectable, carried messages not just about the sun, but about the nature of matter itself. The sun's magnetic complexity increases towards solar maximum and simplifies towards solar minimum. This cycle of complexity manifests in everything from sunspot numbers to the frequency of solar flares. During solar minimum, the sun's magnetic field is relatively simple, close to a dipole, like a bar magnet, with field lines emerging from one pole and returning to the other. But as the solar cycle progresses, differential rotation and convection twist and tangle these field lines. The simple dipole structure breaks down, replaced by a complex web of magnetic loops and arches. Sunspots appear where strong fields break through the surface. Active regions develop, crackling with energy. Flares become more frequent. Coronal mass ejections erupt regularly. The sun becomes magnetically chaotic. Then, around solar maximum, the field flips. The complexity reaches a peak. The polarity reverses, and the cycle begins anew. Gradually, the field simplifies again as the sun heads toward the next minimum. The chaos subsides. Sunspots fade. The corona becomes less structured. The sun quiets down, gathering energy for the next cycle. This breathing rhythm, simple to complex to simple again, has been happening for as long as the sun has existed. It's driven by the interplay of rotation, convection, and magnetic fields, a self-sustaining dynamo that never stops running. And we can see it play out over 11-year cycles, watching the sun transform from calm to chaotic and back again. A stellar demonstration of how magnetic fields behave in rotating, convecting spheres of plasma. Yet the sun has enough hydrogen fuel to continue shining for about another 5 billion years. This gives life on Earth billions more years to evolve before our star begins its death throes. 5 billion years is an almost incomprehensible span of time. To put it in perspective, life has existed on Earth for about 3.8 billion years. Complex multicellular life has existed for less than 1 billion years. Humans have existed for a few 100,000 years, a blink in cosmic time. In 5 billion years, evolution could take life in directions we can't even imagine. New kingdoms of life could emerge. Intelligence could evolve in other species. Earth could be colonized by descendants of current life forms so different, so changed, that they'd be unrecognizable. Or life could be wiped out by some catastrophe, an asteroid impact, a nearby supernova, runaway climate change, long before the sun begins to die. The sun's eventual expansion into a red giant is inevitable, but it's so far in the future that it's almost irrelevant to any immediate concerns. We have time, enormous amounts of time, more time than life has already existed. The sun will keep shining, keep providing energy, keep making photosynthesis possible, keep driving Earth's weather and climate for billions of years. And perhaps, if we or our descendants survive that long, we'll have developed the technology to leave Earth, to colonize other star systems, to ensure that life, whatever form it takes, persists even after the sun dies. The sun's eventual death isn't an ending, it's just a transition, a change in circumstances that intelligent life could potentially prepare for, given enough time, and time is one thing the sun still has in abundance. The sun's gravitational field is strong enough to capture and focus light from distant stars. This gravitational lensing effect could theoretically be used to study objects far across the galaxy. Einstein's general relativity predicts that mass bends light, and this prediction has been confirmed countless times. During a solar eclipse in 1919, astronomers observed stars near the sun's edge appearing slightly shifted from their usual positions, proof that the sun's gravity was bending their light. This bending creates a lens effect. Light from a distant object passing near the sun is bent inward, and if you're positioned at the right spot far from the sun, the bent light converges, creating a magnified image. The magnification could be enormous, potentially thousands or even millions of times, making it possible to see details on distant objects that would be impossible with conventional telescopes. The challenge is positioning. To use the sun as a gravitational lens, you need to be at the focal point, about 550 astronomical units away or farther, and you need to align the sun, the distant object you want to observe, and your telescope precisely. This is technologically challenging, requiring spacecraft capable of traveling to the outer solar system and positioning themselves with extreme accuracy. But the rewards could be extraordinary. We might be able to image the surfaces of exoplanets dozens of light years away, seeing oceans and continents and cloud patterns. We might detect biosignatures, signs of life in distant atmospheres. The sun, which already gives us light and warmth, might also give us the ability to see farther into the universe than ever before. It's a beautiful idea, using our own star as a lens to study others. This sun's future as a white dwarf will leave it incredibly dense, about 200,000 times denser than Earth. A teaspoon of white dwarf material would weigh about as much as an elephant. When the sun sheds its outer layers and the core is all that remains, gravity will compress it to densities almost beyond imagination. The electrons in the atoms will be stripped away, and the atomic nuclei, mostly carbon and oxygen, will be packed together as tightly as quantum mechanics allows. This is electron degeneracy pressure in action. Normally atoms are mostly empty space, the nucleus is tiny, and the electrons orbit at relatively large distances. But in a white dwarf, the electrons are compressed into the spaces between nuclei, filling every available quantum state. The Pauli exclusion principle prevents them from being compressed further. This quantum pressure is what holds the white dwarf up against gravity. The result is an object about the size of Earth, but containing half the Sun's mass. The density is about 1,000,000 times greater than water. A sugar cube-sized piece of white dwarf material would weigh several tons. The gravity at the surface would be about 350,000 times stronger than Earth's surface gravity. If you could somehow stand on a white dwarf, which you couldn't because you'd be crushed and vaporized instantly, you'd weigh millions of pounds. White dwarfs are strange objects, quantum mechanical in nature, held up by a kind of pressure that has no classical analogue. They're the final resting state for stars like the Sun, dense embers cooling slowly over trillions of years, and eventually, in the unimaginably distant future, the Sun will join the ranks of white dwarfs scattered throughout the galaxy, a small, dense, slowly fading remnant of the star that once gave us life. The Sun's energy output has remained remarkably stable for billions of years, enabling life's evolution on Earth. This stellar steadiness is one reason Earth has remained habitable for such a vast stretch of time. Many stars aren't as stable as the Sun. Young stars flare violently and unpredictably. Some stars pulsate, and brightening and dimming over days or weeks. Binary stars can have complicated interactions, exchanging mass, creating outbursts. Even among single main sequence stars like the Sun, there's variation. Some are more active, producing more flares and having larger brightness variations. The Sun is fortunate in a sense to be so stable. Its 0.1% variation over the solar cycle is tiny compared to what it could be. This stability has been crucial for Earth. Life evolved slowly, and over billions of years. Ecosystems developed, became complex, adapted to gradual changes in climate and environment. If the Sun had been variable, if it had brightened by 10% for a few centuries, then dimmed by 10%, then brightened again, Earth's climate would have swung wildly between hothouse and icehouse conditions. Life would have struggled to adapt, but the Sun was steady. It provided a reliable energy source, day after day, year after year, millennium after millennium. And in that reliability, life found the stability it needed to flourish. The Sun's gift to Earth isn't just energy, it's consistent energy. Predictable enough that evolution could build complex systems adapted to particular temperature ranges, particular light levels, particular seasonal cycles. We owe our existence not just to the Sun, but to the Sun's steadiness. A more variable star might have created life, but probably not complex life. Certainly not civilizations capable of studying the star that created them. The Sun's calm, patient shining over billions of years is one of the great cosmic gifts, often overlooked because we take it for granted. The Sun rises, the Sun sets, every day without fail, And in that reliability, everything else became possible. The Sun's death as a planetary nebula will create beautiful shells of glowing gas visible across light years. This stunning display will mark the transformation of our life-giving star into a slowly cooling ember. When the Sun becomes a red giant and begins losing mass, it won't happen all at once. The outer layers will be shed gradually, pulsing outward in waves driven by thermal pulses in the helium-burning shell. These expelled gases will expand into space, forming a shell around the remaining core. And when the core finally becomes a white dwarf, it will be incredibly hot, up to 100,000 degrees. The intense ultraviolet radiation from this hot core will illuminate the expanding shell, causing the gas to glow in brilliant colours. Oxygen will glow green and blue, hydrogen will glow red, nitrogen will add purples and blues. The result is a planetary nebula, a misnomer since it has nothing to do with planets, but named that way because early astronomers thought they looked like the disks of planets through small telescopes. Planetary nebulae are among the most beautiful objects in the universe, glowing shells and wisps and filaments of gas, painted in vivid colours, expanding slowly into space. The Sun's planetary nebula will last only about 10,000 years before fading. The gas will disperse, mixing with the interstellar medium, enriching it with carbon and oxygen and other elements created in the Sun's core. And eventually, that enriched gas might collapse to form new stars, new planets, perhaps new life. This Sun's death will seed the galaxy with the building blocks for future generations. It's a fitting end in a way. The Sun formed from the debris of previous stars. It will die and contribute its own debris to the cosmic cycle. Life, elements, stars, all connected, all part of the same great recycling program. The Sun's death won't be an ending. It'll be a transformation, a passing of the torch to whatever comes next. The Sun contains nearly all the angular momentum and mass of the solar system, yet took billions of years to form the complex system we inhabit today. From a collapsing cloud to a life-sustaining star, the Sun's story is inextricably woven with our own existence. When the solar nebula collapsed 4.6 billion years ago, it carried enormous angular momentum, the rotational energy of the original cloud. As it collapsed and spun faster, most of that angular momentum should have ended up in the central object, the Sun. But it didn't. Through a combination of magnetic fields, friction in the protoplanetary disk and gravitational interactions with forming planets, much of the angular momentum was transferred outward. The Sun ended up with 99.86% of the mass, but only about 2% of the angular momentum. The planets, tiny in mass, carry most of the system's rotation. This transfer was crucial. If the Sun had kept all the angular momentum, it would be spinning so fast it might have torn itself apart, or remained too hot to allow planets to form nearby. Instead, with the angular momentum spread out, allowing a stable disk to form, allowing dust to coalesce into planetesimals, allowing rocky planets to form close to the Sun and gas giants farther out. And so, over millions of years, the solar system took shape. The Sun ignited at the centre. Mercury, Venus, Earth, and Mars formed from rock and metal. Jupiter and Saturn gathered vast amounts of gas. Uranus and Neptune formed farther out, where ices could condense. Moons formed around planets. Asteroids and comets filled the gaps. The sun is the heart of this system, the anchor, the energy source, but it didn't act alone. It shaped the system and was shaped by it. The sun's story is our story. We are children of the solar nebula, formed from the same cloud, orbiting the star that ignited at its center. Everything we are, everything we've ever known, exists because a cloud of gas collapsed 4.6 billion years ago and the sun was born. And here we are, billions of years later, and looking up at that same star, trying to understand it, trying to understand ourselves. The sun gives us light, warmth, energy, and life. But perhaps its greatest gift is simply this: the opportunity to wonder, to question, to seek understanding, to look up at the sky and ask, what is that bright thing? Where did it come from? How does it work? And in seeking those answers, to discover not just the nature of the sun, but something about the nature of the universe itself. And so we arrive at the end of our journey through the sun's story. 100 facts, each one a glimpse into the nature of this magnificent star that has been our constant companion for as long as Earth has existed. The sun is many things. It's a furnace, converting hydrogen into helium, mass into energy, through the same process that powers nuclear bombs, but controlled, sustained, lasting for billions of years. It's a timekeeper, that rising and setting with such regularity that civilizations have measured their days and years by its movement. It's a life giver, providing the energy for photosynthesis, driving weather and climate, making Earth habitable. It's a dynamic, changing object, never quite the same from one moment to the next, its surface churning, its magnetic field twisting, its corona shimmering in the darkness. And yet, for all its power, for all its immensity, the sun is also ordinary. It's a medium-sized star in a medium-sized galaxy, one of hundreds of billions. There's nothing special about it, astronomically speaking, but to us, to life on Earth, it's everything. It's the center of our world, literally and figuratively. We orbit around it. We depend on it. We exist because of it. Perhaps that's the most profound thing about the sun. It's both extraordinary and ordinary, both unique and commonplace, both essential and just one star among many. It contains contradictions, the mysteries, wonders, and in trying to understand it, we understand something about ourselves, about our place in the cosmos, about the forces that shape everything from atoms to galaxies. The sun will outlast us, almost certainly. It will keep shining long after humanity is gone, whatever form our going takes. And eventually, billions of years from now, it too will die, expanding into a red giant, shedding its outer layers, leaving behind a slowly cooling white dwarf. But that's so far in the future it's almost like science fiction. For now, for the foreseeable future, for billions of years to come, the sun will be there, rising in the east, crossing the sky, setting in the west, warming the earth, making plants grow, creating weather, powering life. So tonight, as you drift off to sleep, perhaps you can think about the sun, resting just below the horizon, waiting to rise again. Think about the fusion happening in its core, the photons starting their long journey outward, the neutrinos passing through everything, the magnetic fields twisting and reorganizing. Think about the fact that you're made of atoms forged in stars like the sun, that you exist because of billions of years of stellar evolution, that you are, in a very real sense, the universe becoming aware of itself. And maybe that's enough. Maybe that's all we need. The sun shines. We exist beneath it. And for this brief moment in cosmic time, we have the privilege of understanding at least a little what that means. Sleep well. The sun will rise again tomorrow. It always does.